We will start in 30 minutes.
Good morning.
Hello, Jessica.
So I'm almost here.
Yeah, we have time. It's 24 minutes to go.
I know, so that's why I just woke up though. So
Excellent. These are the amazing things about many time zones, right?
oh, I know. I'm like not used to this, but it's I got my applause. Let's see. Oh, there's more applause. Come on, play applause. I need to read those. Anyway, let's see if I got those.
Yeah, that sounds a little bit creepy.
That one did, yeah.
Okay,
this worked before. I'll play with it a little bit here. I just downloaded the. Do it on my phone.
Oh yeah, that will work as well.
I have two screens, a laptop, and a phone. So I'm this is my normal, like, and there's actually the iPad's not here, but there's an iPad too. And this is my home office. And then I've got a clock in front of me with, actually, I should make it, let's see if we can do that. Let's see, this is a computer display, universal time. Oh, just a second. I just turned on another one of my Alexas. Computer, turn off. The problem about having a small house is if you say something, I've 4 different Amazon Echoes and 3 different names I can use. Computer, display, universal coordinate, time.
I couldn't find that video.
Computer, show universal time.
I couldn't find that video.
Ah!
Technology.
Yeah, well, it sometimes works. I don't know whether I have, maybe Google could do it, but I don't have a Google display. Let's see. So what I'm trying to do is find the applause thing. Okay. Go to speakers. Probably. Yeah, these are all from this morning. Okay. 46 new messages since I looked at it last night. Okay. Okay, what I want is applause. Define. Let's go. How's C.
Okay, we have Kai already as a panelist,
Okay.
Jan as well. He will be organizing the both later on today.
Do I introduce him or am I off by then?
Yeah. You can definitely introduce them all. We start in 19 minutes, so there's still plenty of time. But
Yeah. Oops. Oh, try again. Oh, okay. My fingers are too fast. Okay, let's try this. Got it. Okay. How's that?
That's good.
Okay, then I'm set. Let me plug it in so the battery doesn't run out. Also, I have all these different cords for charging things sitting here.
Yeah,
I
we
have this
have all
great,
this.
this great thing on. It's on top of my desk behind the screen. It's got like both USB ports and power ports inside. That's exciting. There we go, 11 UTC. There's the time, YouTube Live. Yeah, I decide whether I want to watch some of it. I have a big TV in my living room, which I can do YouTube on. So.
Yeah, I see that a lot of people are using YouTube actually. And I've seen that already at other conferences that people just, put the conference on their TV.
Yeah.
And they really like it. Or maybe some people with a projector also do that.
Ooh, that's cool.
Which is really cool.
Yeah, I thought about that. I could, if my basement was as clear as I want it to be, I have a big wall that I could hang my screen on. I do it on my shed in my backyard when it's warm, and I have a laser projector, which has it has everything. It has a memory stick on it with or a USB stick that has everything as Google TV, so I can download apps to do streaming. I watch too much TV. It's been what I don't do it that often, but I did have to admit I started binge watching a show on the weekend, and I think on Saturday I watched 5 hours of this one show. So
yeah, I usually don't get into shows myself, but I know friends and also my wife do get hooked.
Yeah, no, I do that. I go through one at a time and usually get hooked on one thing and watch like an episode or two every night for a week. And then, although this one, it turns out it went. I hate doing this. Is getting hooked on a network show where there's like 3 seasons of 20 episodes each, and if it's pretty well written, it's hard to not watch it. I like 5-episode things a lot better, and that's the other thing I'm watching now is a 5-episode show. I just watch 1 episode of that every night, and I go from show to show. But I think a lot of it's been nervous watching over the last week here. So now I'm.
Yeah. Now it's more calm, I guess.
Yeah.
Calmer.
Oops.
Yeah.
Wait a second. Why is it not?
So, folks, we're starting in 15 minutes. I will also send out a reminder on Discord. And Jessica will be the session chair. And so she will be introducing our speakers. And I'll stay in the background.
Oh, I think the reason the sound got weird is because.
Yeah, so
There we go. Okay.
So we decided to change a little bit the schedule. I have a question from Erica on Discord. She's totally right. There was a change in the schedule, which reminds me of an announcement, a public service announcement, folks. We will have from time to time some changes in the schedule. Some somebody might not show up, or we might have to switch two talks. And talking within the LOC, we decided to make a change in the schedule. In that I announced that at the end of this morning's session, but not everybody was online, of course. So we repeat it here. We decided not to repeat the videos for this morning, welcome address and logistics video. I will just be saying a few words in probably 5 minutes just before we start with the session. You can always watch those presentations both on on YouTube. The logistics was also is on YouTube. It's public to everybody on the ADASS channel. I will also put a link in Discord later on. And if you want to watch the address, the welcome address from IRAM and the Istituto de Astrofisica d'Andalusia, you can also watch it on the YouTube stream. But we thought that we would just leave a little bit of a longer break and not repeat those information over and over again. So I will say a couple of words about logistics very quickly anyway at the beginning of this session before Kai's talk. So in 2 minutes, I guess, at 10:55 UT. And I will also put the link on the Discord channel.
Okay, so I have Kai Polster and Kai Polster screen. So how is that going to work, Kai? I don't hear him.
Hi, Jessica. It's Kai Polsterer.
Hi, Kai.
Kai Polsterer's screen is just Kai Polsterer's screen is just there to see what's happening.
Okay. Oh, okay. Good idea.
I need the output signal as well as a stream signal.
Okay. So do you need to be unmuted?
Kai Polsterer is the right one.
Okay. Yeah, I can hear you now. So. Okay. So you want the one you're watching to be muted and the other one to be not muted. So Kai, do I just say you're from HITS or what's the?
Yes, please, Jessica. What did you say?
I said, do I say you're from, I mean, I'm gonna say what you do, but do I say from HITS or what? HITS? Okay,
No,
just say
HITS.
HITS.
It's
Okay.
like music, yes.
Right, I'll say
But
that.
just in
Okay.
science.
Right, hits in science. Okay, I just wanted to be able to know how to do that. And then I know you're great at, you have both computer science and physics and astronomy and instrument control too, which is an
Physics is the
interesting.
natural science that studies that.
Yes, that's right. In the past, I did a lot of near-infrared instrumentation with Lucy. Yes,
Yeah. So that's an
that's how I
interesting set.
started to come to ADASS in 2003 in Glasgow was my first one.
Oh, that was a good one.
Yeah,
That's one of my favorites.
absolutely.
That's the first one we had 2-hour
I
lunches.
still remember the lunch being served
Yeah,
with
yeah.
waiters and opening the dishes. Yes.
Oh, what a feast. Actually, I remember the lunches more than I remember the actual sessions, I'm afraid.
No, I was
I do
still
remember
very
good stuff
impressed.
there.
I think Mr. Wallace came to me and asked me some questions about my post I was presenting.
Uh-huh.
And he was, yeah, impressive person, I must say.
It's actually the only conference I met where I've met Mark Calabretta, I think. And
Okay.
World Coordinate System guru extraordinaire.
Yeah. Oh, I see.
Whose software I
So give me a
use.
few seconds to get ready.
Okay, I'm ready for you, waiting for you.
Yeah, just give me a few seconds. I'm ready by 12 sharp or 11
Good.
UTC sharp.
Okay, got it. 6 a.m. here.
That's early.
Yeah, it is. I got up amazingly quickly. I was surprised. There. I feel dressed. Okay. Oh.
Okay, so I will just say a couple of things about logistics. We made a small change in the schedule. I sent out an email, well, an email not, a message on Discord to everybody. Remember that you can always get the latest and up-to-date schedule on the website, or if you subscribe to it in your calendar application, you can always get it up to date. We plan on doing no other changes in the schedule, but you never know, right? We might have to swap 2 talks, or somebody might not show up, or we might reschedule. It's a live conference after all. Anyway, just for the people who are not aware of this change, which I mentioned at the end of last session in the UTC morning, we have taken the logistics video about the website, about Discord, about Zoom, and put it public. It's public for everybody on YouTube. And I sent out the URL on Discord. If you don't see that message, it's easy to find. Go to youtube.com and search for ADASS 2020, and you will find it. You will also find the channel, the ADASS 2020 channel in there, where we will publish all the edited and cut videos as soon as possible, and after the conference. It will take a little while, I will warn you. So logistics, I guess the most important thing to say about logistics, and I go in more detail in that video, it's a 9-minute video, so it's very quick, is Discord. Discord is the piece of software that ties all our infrastructure together, and it can be overwhelming. You know, it can be totally overwhelming. So I guess I should, since I'm talking, I should also show my face. It can be a little bit overwhelming at first, especially if you're not used to it. But once you get you know, used to it a little bit, you realize it's a very powerful piece of software. So you can use it to chat with people, to find people, to get the YouTube and Zoom links, clicking at the top of the Talks channel and the top of the window of the Talks channel, Command K if you're on a Mac, Control K if you are on Windows or Linux, lets you jump directly to a person and chat directly to that person, or jump to a given channel. So give it a try. You can also find lots of information about Discord online. And now I will leave the floor to Jessica, who is our session chair for this session and the UTC afternoon, I guess, and East Standard Time morning, early morning. And
pre-sunrise.
Pre-sunrise. And she will introduce our next speaker, and we're all very excited about hearing what's up.
Okay. So our first speaker this morning, our invited talk is by Kai Pulsar on from photometric redshifts to improve weather forecasts, an interdisciplinary view on machine learning in astronomy. Kai comes to us from HITZ in Germany. And he's had this interesting background of physics, astronomy, computer science, and building instrumentation, or working on instrumentation. So he's done a lot of different things. And now he's really our guru on machine learning. So you can take it away, Kai.
Yeah, many thanks, Jessica, for this very warm introduction. And as you can see, yeah, it's a little bit frustrating not to be in Granada, but I thought to make the best out of it and invested travel money in a professional video team supporting me. So Brennex Films now realizes the presentation of me today. So first of all, good morning, good afternoon, good night, and good day to everyone listening. Yes, it's many time zones we are bridging, and it's definitely different times and difficult times with Corona being around, but I seriously hope we will meet soon again. So when I was invited to give a talk at ADASS, I was really happy when I heard it's going to be virtual. I was a little bit of upset, I must say, but seeing how much effort was put in the presentation and preparation of the presentations online and how well we were trained on the presentations, I really have to thank a lot to the local organizing team as well as the program organizing team making ADASS happen in a virtual way. And I will especially have to thank them after the conference because I think it will be the best virtual conference of this year. So yeah, today I want to talk a little bit about photometric redshift estimation and how this helps to improve weather forecast. I thought it's good to give a more interdisciplinary view on what actually combines different sciences, and it's machine learning. It's methodology that is similar to many different fields. So whatever we do, we often have to think of what is the use case we are talking about, and there are connecting bridges if you think about what are the methods you apply to your data. So in this example, I'm talking about supermassive black holes on one side, because those are the sources we want to observe in a photometric way, where we want to estimate redshift photometrically. Those are supermassive black holes, and they are accreting material, and thereby they are amongst the brightest sources in the universe. That allows us to observe them at really large distances, and this allows us to get insights into the early universe. But how does this connect to weather on Earth? There might be probably some relations, but the relations here lie all in the methods we apply. So let's talk about what you always have to talk about when you talk about machine learning. Do we actually have too much data? And what is the solution if we have a lot of data? So what kind of data do we have? At the moment, we already have Gaia. That's something like a petabyte of data. The mission is still flying and it's collecting a lot of data. But we also have not only missions in space and instrumentation on Earth, we also have simulations. And the illustrious simulation, for example, delivered also a petabyte of data. And if you think about the upcoming SKA, yeah, it will be 1 billion gigabyte, an exabyte per day. So we are really talking a lot of about a lot of data. And what we need to deal with it is another way of analysis. Machine learning actually could be key to improving the way of analyzing the data. We can take away the necessity to do things manually, where we actually could use computers and train computers to assist us. But how do we do so? Yeah, one typical problem we are facing is solving regression problems. By looking now at this equation, you see it's something very simple. But what we want to do actually is we take a large catalog, and from the catalog, as you see in the equation, yeah, we sort of have our model. We build our model. This is our regression model that helps us doing the analysis. In our regression model, we put our features. This is the data we collected through our catalogs, our surveys. And what we want to do, we want to predict values. Values we want to use for a scientific analysis. Those values could be of different kinds. In this example, I'm doing regression of real values. So in the example I was talking about, it's about estimating the redshift of a source. What is redshift? So people often combine or compare redshift to something like the Doppler shift. That's not the right picture, because while light is traveling through the universe expands, and thereby the wavelength gets extended. This is a so-called redshift. And as you can see on the equation, in the equation you see how the wavelength, the rest frame wavelength is compared to the observed wavelength, and this gives you actually the redshift. In this example, you see two spectra of two different quasars, one quasar at a redshift of 3.8 and another one at a redshift of 5.8.
We've lost Kai, at least here.
Yes, I think we lost Kai. Okay, so Kai can hear us.
Can we unmute Kai's second screen?
So Kai can, I'm chatting with him on Discord. Kai apparently can absolutely hear us.
Hello?
Oh yes, now we can hear you. There is feedback, but we can hear you.
You hear me better now?
Now, yes.
Oh, jetzt höre ich nichts.
So folks, just a few technical glitches, but hey, this is a live conference, so we'll be back in no time. Okay, Kai's connection seems to have some problems, so we'll see if we can fix it in no time, and otherwise we can always. Okay, Kai tells me that he will be back in a second, so there is a great moment for me to just tell you a bad joke. Okay, bad in the sense that they're not funny. Okay, Kai is here. Well, no joke. Kai, we cannot hear you. We can see you.
Can you hear me now?
Yes.
Oh, yes, yes.
Ich bin auf dem internen Mikro.
You're a little bit on the low side, but we can hear you.
Now you see me?
Yes.
Yeah. It seemed my laptop overheated. It got redshifted by a few degrees, sorry. We switched to a different machine, so we are online in a second.
Okay, so I can tell my joke, my bad joke.
Yes,
so, you know, folks, I got this friend, you know, very nice guy, and he works as a farmer, and he's a very good farmer. And I would even say that he is outstanding in his field. Ha, 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 ha. Ha, 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 ha. So I'll wait a little bit. I'll wait a little bit before getting to the next one.
Okay, I'm ready.
Cool. Take it away, Kai.
No more jokes. Yay.
Oh, yeah, sorry. Believe me, I'm sweating like hell. So I
Kai,
have to catch up the time. No worries.
No, we can give you some more time because there is a break after you.
No. Yeah, but the laptop overheated and I had to switch the machine. That took me 3 minutes, sorry. Or
Go for it.
So as you can see, as I said, the Lyman alpha break of the low redshifted quasar at a redshift of 3.81 is in the R band visible. You see in the background the filter bands of the Sloan Digital Sky Survey. And the Lyman alpha line is of the high redshifted one in the I band. If you now look at the images, then you see actually what the task is. The task is, by looking at images, we want to estimate what actually the proper redshift of those sources is, just by using photometric features. And as you can see from the spectra, redshift is usually determined by taking spectra. But taking spectra takes a lot of time, is instrumentationally very challenging and difficult. And therefore, the point is, we want to estimate certain physical properties.
Kai, excuse me, we don't see your slides. We don't see your screen.
You need to share your screen.
Gehen die Slides nicht raus? They should be in my video, actually. If you check my video, you should see them.
We're seeing them, but we're not seeing them on the full screen.
Yeah.
Don't share my full screen, just leave my video open as it was.
Yes, that's the case. We didn't change anything here. You should be, I'll try again, spotlighting you. We seem to have lost.
Hello? No, I'm here. I'm sharing my screen. I'm sharing my slides.
Okay. We can see that you are sharing, I mean, you're, broadcasting your video and your audio, but it is true, there is nothing coming out. And on the main screen. Okay, so I'll try to stop your video and start it again. Let's see if maybe this does the magic.
I'm showing up on YouTube, and I'm not sure how that's happening.
Okay.
Yeah.
Okay, now we see you, but try to speak, try to say something.
Hello, hello, hello.
Echoing.
Can you hear me?
Okay, maybe. Now we can see you. Try again.
Yeah. Give me a second. Ich share die Folien jetzt von hier. Okay, das haben wir keine. Do you now see my slides?
Yes.
And you can hear me?
Yes, there is an echo, but we can hear you.
And you see my slides?
Yes, and we can see your cursor. Only thing is that there is an echo when you speak, but apart from that, we can see the cursor, we can see the slides, and we can also see you in the smaller window, like the person type of camera. As somebody mentioned, it could be that Zoom thought that your presentation were the secondary view, so to say.
Höre ich nichts. Can you hear me, Francesco?
Yes, now we can hear you fine.
Because I can't hear you.
Okay.
I hope you see my slides, and I hope you see my presentation at the moment.
We do.
Is this correct? Okay, so I keep on talking now on another machine, even the third backup. Okay, you see my slides and you can hear me, I hope. Good. Okay, so yes, the photometric redshift estimation we spoke about. What you see is what we need training data is essential in principle. If you want to do machine learning, you need training data. In this example, you see a plot of the spectra taken in the quasar spectra taken in Sloan in an early data release 3. And what you can see is distinct lines moving through the different wavelengths. So you see the Lyme alpha, you see the magnesium line, you see all the different lines as they slowly move from a low redshift at 4,000 angstrom to a higher redshift at 9,000 angstrom. So photometric redshift estimation is not complicated. I spoke about it at different ADASSs in the past. So if you use a simple k-nearest neighbor model, this is by looking at certain features, looking how certain sources look like in the high dimensional feature space, you can select objects in the vicinity of a source just by comparing them feature-wise. Those with similar features appear to have the same physical mechanisms. So by just calculating the mean over objects in their vicinity, you can estimate a regression. So what we put in the past were magnitudes. Magnitudes in principle are taken in Sloan as point spread function magnitudes, also model magnitudes that are the best out of the Dever-Couleur fit or search profile fit. And what we got out were redshifts. So data in, training a model, predicting redshifts as a regression task. Crucial when you do machine learning is the question of how do you evaluate performance. So there are many different scoring functions. You take the root mean square error to compare your estimated value with actually the true value of a source determined in a spectroscopic way. You calculate something like median absolute deviation. You look at biases, standard deviation, max errors, mean errors. You look at how much they spread. You look at a lot of different values in there to estimate actually how bad the error is. And you have a lot of multiple diagnostic tools actually to look at the data in a visual way. And in this plot on the right-hand side, you see the spectroscopic redshift that's considered the true redshift being plotted against the photometrically estimated redshift. Here in this example, I used the k-nearest neighbor model with the 7 nearest neighbors being considered for the estimation. And as you can see, the perfect result would be a direct line going through the diagonal. There are some errors in there. But the question is, what about uncertainties? What we need to take care about are uncertainties, because being uncertain about certain things helps us to be more precise. You will see in a second what I mean with this. So we have uncertainties in our model. They come from, do we have a representative data set for training? Do we actually have the right algorithm chosen? Is it able to generalize well to the problem at hand? A lot of different things are here to be considered as model uncertainties. We have input uncertainties, measurement errors that occur while doing our experiments. And those input uncertainties, of course, influence how good we can and how precisely we can estimate a certain value. And therefore, we should have uncertain estimates. If you now take your model uncertainty, your input uncertainty, and your uncertain estimates you want to produce, you are taking the step going from predicting a single redshift, in this example, a redshift of 0.1234, and you want to go to something like a probability density function where you actually predict a probability density that tells you how likely it is for a given redshift that this redshift is a correct redshift you want to have. Probability density function have a lot of nice side effects. So if you represent your result as a probability density function, you can take two distinct values, A and B, and you can just estimate or calculate what is the likelihood given a value of A, given a value of B, or by just integrating over the probability density function, you get a probability out. You really can estimate how probable it is to a certain percentage that something is in between a certain range. And that makes your science stronger, because now you can say, not only give me quasars with a high redshift, you can say, give me those quasars with a redshift above 5 that have a probability of being above 5 of more than 90%. And that makes you more precise in the way you analyze and the way you inspect your data. The challenge here is multimodalities. What you see in the plot is at the upper edge, the individual values, redshift values of the nearest neighbors with respect to the photometric features. And at the lower bar, you see a histogram that tells you what are the frequencies of certain values happening. And what you see now is the true redshift is a red line somewhere around 2, but you see there are 2 peaks. We have a multimodality. So our model, a nearest neighbor model, would say our source is either something around 0.5 or something around 2, but nothing in the middle. Evaluation tools, as I said, are very important. But what do you do if you have such a multimodality? The root mean square error is a proper score, but it's in the middle of 2 peaks. In this example, I plotted 2 peaks. One peak is perfectly aligned to the true redshift of 3.45 of that example. The other peak is at a different place. But if the data doesn't allow you to clearly state it's either A or B, you have to be able to give it a soft answer. In this example, it's saying it's A or B. But if you now take the root mean square error, you're looking at a value in the middle. And as you can see, the likelihood is really small at that point. So you don't take the shape and the overall structure of your probability density function into account. You're just condensing it down to a single value. So the question here is really, is this a proper tool for analysis? Another thing I see quite often is that people start stacking PDFs. In this example, on the left-hand side, you see very narrow and precise estimates. It's like saying tomorrow is the temperature 15 degrees plus minus 0.0001. You all would know I'm lying at you because I cannot precisely predict the temperature of the next day. So it's lying at you. But if you now start stacking them and define outliers to be outside of a certain area, you see in the plots above that the likelihood is close to 0. And in the example further to the right, the likelihood is increasingly higher, but the overall result tells you there are a lot of outliers. That's not true if you have multimodalities. So the question is really stacking PDFs. Is this the right way to evaluate? So back then, when we were working on photometric redshift estimation, we came along the continuous rank probability score, the CRPS. And the CRPS is a nice tool that allows you, with a single score, to measure how sharp a prediction is and how well calibrated it is. I show you in a second what this means. So given a probability density function, in this example, the black is a predicted probability density function in the redshift space. And specified is the mu and the sigma of a Gaussian prediction in this example, and the true redshift of 2.2. Then you just take for the CRPS, you transfer the PDF by integrating to each individual value. You transfer the PDF into a cumulative distributive function. And now you can look at the true redshift at Z equals 2.2. The true redshift itself turns into the Heaviside step function. And if you now integrate between the Heaviside step function and the CDF of the predicted redshift distribution, the probability density function of the predicted redshift, you get the CRPS. So it's visually quite obvious what you do. So taking all together, now you see the equation is not so complicated. You just take 2 CDFs, the one of the true redshift, the CDF of your prediction, you combine both with each other, and then you integrate over the surface area in between. Another nice tool is a PIT, the probability integral transform. It's a visual tool to actually see how well your predictions are calibrated. If you take the CDF at the upper right and evaluate it for each individual estimate at the true redshift, you get a value between 0 and 1. If you now take those values for all your estimates, you get something, you get a histogram representation. And in this example, the PIT tells you it's underdispersed. So if your predictions are too narrow, as I made the example with temperatures, you always hit zeros and you always hit ones because your estimate is too narrow and the wings of your prediction will never catch, only the wings will be hit. And then you get an underdispersed image of your predictions. You are over dispersed if you would say tomorrow the temperature will be 10 degrees plus minus 30 degrees. You always sort of hit it, and therefore you always hit values somewhere in the middle of the CDF around 0.5. If you're over predicting or under predicting, you get a bias term in, then it's slanted. Only if it's well calibrated, you get a nice line. So now let's apply what I told you about evaluation tools to our example I showed you in the beginning. We use k-nearest neighbors on all the quasars in the Sloan Digital Sky Survey. If we now say the mean value of the k and n gives us the mean of a single Gaussian of our probability density function, then the sigma is just an arbitrary value we choose. So saying our uncertainty is 0.01 in our predicted space gives us a horrible PIT. We are completely underdispersed. We are just saying we are absolutely sure about our values, but we are lying about the precision of our uncertainties. Therefore, the CRPS is high as well. If we now say, okay, then our estimate is worse. Let's say we have a single Gaussian with the value of 0.2. We slightly improve, but we are still not telling the truth. And this is what the PIT and the CRPS shows you. If you now take a single Gaussian and calculate a standard deviation over all the nearest neighbors, so you take the nearest neighbors to calculate a mean value, and you use them to calculate a standard deviation, you get an adaptive sigma. And it's improving step by step. And if you compare the results, you see from being lying about uncertainties, making them worse, going to an adaptive sigma, you improve slightly your performance. But it's not correct, because what I told you in the beginning is we have multimodalities in here. And multimodalities mean it's not a single value, it can be multiple values. And what to do about multiple values? We need a different representation. In this example, and as you could see here on the slide, you use a Gaussian mixture model to actually represent your estimates. You take the results of your k-nearest neighbors and fit a Gaussian mixture model to allow a multimodal representation. If you do so and use a Gaussian mixture model with 5 components, we use the Ikaike information criterion and the Bayesian information criterion to evaluate a good number. Some people would say 4 is better, some people would say 10, but I say 5 is a good number, and actually it doesn't matter really. But if you look at it, you see, taking the multimodalities into account, the plot completely changes in the way it's representing. Now it's no longer plotting the true redshift against the estimated redshift. It's on the y-axis, it's probability density functions. And so you see some probability density. And now from the plot, you can see that redshifts of 0.7 have also a likelihood to be mistaken as redshifts of 2. And this is the multimodality I was talking about. If you now use a random forest, take the individual results of the individual decision trees in your ensemble, and you combine it with a Gaussian mixture model, you have something like a quantile regression forest, you further improve. And as you can see, the PIT becomes more and more evenly calibrated, homogeneously calibrated, and the CRPS is dropping as well. So if you now compare them, we are going further steps. So from single estimates, single Gaussians, to multiple Gaussians. But what is the next step? The next step is talking about learning on images. And here the IVOA is a great help. And I can tell you, besides the trouble I'm having today with computers, and believe me, I'm sweating like crazy with all the problems getting the presentation starting. Last Friday, I was working together with colleagues in medicine. And yes, thanks to all the gods of you who invented FITS, who invented meta information and common standards. I'm freaking out getting TIFF images, and no one can tell me how they observed, what they observed, at what resolution they observed, and there are no logs at all. And then you have a mess of data. We have the International Virtual Observatory Alliance with heel pigs and hips, and those tools like hips to fits and hips by Thomas Boch is having a nice post on that, by the way. We now can access all the huge data sets in a uniform way, and we can do deep learning on massive data sets. And that's what we did in the past. This all goes back to work done by Antonio Di Santo while he was doing his PhD thesis with me. So we took a deep convolutional neural network, and at the end, we used a simple mixture density network. A mixture density network is a fully connected network that just takes the learned features out of the deep convolutional part and uses those to predict a set of mu, sigmas, and weights. And those values are actually what you need to define a Gaussian mixture model. So by doing so, we were now able to take images as input and produce a Gaussian mixture model, a PDF as prediction. So when we trained a simple mixture density network just on the pure features, just the later part, taking the photometric features, you see we get nearly a perfectly calibrated PIT, and the CRPS dropped by another order. And now take into account the plot is now showing the log sum probability density. Otherwise, it would look like a tiny line in the center and being very precise about the multimodalities. So this is really showing when using a proper scoring rule, when training a network with a proper scoring rule, you improve your performance tremendously. So what happens if you take images? You further improve it because you now access the full range of photometric features encoded in the images. It's not only that you take the pre-extracted features, it's really that you take all content of information from the image and extract it to build a PDF. And as you had seen now, with proper training and proper uncertainties, you get to much better and honestly calibrated results. So if you take those things now and you want to know my age, and you take a picture of myself and a picture of a dead rotten fish, you see the picture of myself tells you my redshift is 1.7, so I'm roughly 10 giga-years old. And the rotten fish is roughly 3.5 giga-years old. And of course, that's correct because a fish doesn't live as long as a human. So it tells us there are a lot of limitations. A network trained to do a certain task cannot be used for a different task. Now let's quickly jump to the weather forecast. How is all the things from photometric redshift estimation of quasars, rotten fish, connected to weather forecasts? In principle, through methodology, as I said. In this example, we took data from the European Center for Medium-Range Weather Forecast. And this is a lot of data. On a dense grid of 81 by 81 cells, you have 18 physical parameters. And now in the weather forecast simulation, you don't run a simulation once, you run it 50 times in order to deal with the uncertainties you have in the input data, you have in the model, to get a better description of what the weather will be next day and whether you are going to have a barbecue next day. So what people do is they do statistical post-processing. They interpolate out of the grid for each individual stations where you have latitude, longitude, altitude, orography. They interpolate the values, and now on a 48-hour lead time, they want to forecast just the temperature for the next day. And this post-processing is necessary to deal with systematic errors. With the best method on the used data set, using the years 2007 until 2015 for training and 2016 for testing, with the best method so far, people could reach a CRPS of 0.81. So what they now used, because we learned about the CRPS from the weather forecasting people, and the weather forecasting people thought, oh, the way you train neural networks with CRPS and you use it is similar to what we do in our post-processing. So they took just the fully connected part, the mixer density network part on their data and improved it. And with this, they were able to further reduce the CRPS to a value of 0. Oh, I can't see it on my screen, 78, I think. It was a little bit lower, yes. You also can do a lot of nice things now with the data. You can use some things to project the data. Just to give you a view, you try to squeeze down the parameters of all individual stations. You project them to a 2D plane, you color based on the 2D plane, and then you can start to have an interpretation, and you see bigger cities and the Rhine Valley here in Germany have different correction terms they require. And future and ongoing work is currently, we are now using locations, we are using a compressed view of the cloud image, of the dew points, of the temperature, of the pressure regime, to sort of understand what is the overall weather regime in Europe, condense it out of the complex things. And current experiments indicate that we even can go to a CRPS of 0.76. So we are further improving just by having this collaboration between people in astronomy and people in weather forecasting and statistics. And now, not to blast the whole thing, coming to the conclusion, probabilistic photometric redshift regression is something essential in astronomy because it's essential for cosmology, and we need to do it in order to understand the early universe. But what we were lacking at the beginning was a proper evaluation. And here, discussion and input from statisticians who were dealing with uncertainties in weather forecasting helped us a lot. So we used then, and we were the first actually, to use the CRPS for the evaluation and as loss function for training of a deep convolutional neural network, of a neural network in general. Now, a lot of other people use it in biomedical applications because it's really something like a truth serum, enforcing that you're not lying about your uncertainties. Then we had everything and we gave our code away to the statisticians, and they used it to now do post-processing for the weather forecast simulations. So just to conclude, uncertainty is necessary to be more precise. It seems a little bit awkward, but by giving uncertainties, people can be more precise in how much value they put to certain estimates and certain values. Choosing the right score for training and evaluation is essential because this allows you to put a focus on specific things you are interested in. And the root mean square error, even though we constantly use it, is not the best way to do it. Data science is very interdisciplinary, so let's learn from each other. So I would like to acknowledge Antonio Di Santos, Sebastian Lerck, and Tilman Gneiting. Those are the ones at HITS we were working with, and most of the work on the astronomy side originates from Antonio Di Santos' PhD thesis. So many thanks for the fruitful collaboration, and thanks for your attention. And now I just need to get my sound running, and I still do not understand why I can't hear anything.
So if people have questions,
Hello,
they can.
hello.
Hello?
Can someone say something?
I'm talking. This is Jessica. Can you hear me?
Yes, I can hear you. Yeah.
Oh, good. So if people have questions, we'll take a couple minutes for them. We've got 5 minutes till we start the next session.
Yeah, I'm so sorry for the.
So anyway, you can raise your hand on Zoom. I'm watching there, or you can ask on Discord. Let's see. Mark Taylor asks, as a result, PDF is harder to work with than a mean plus standard deviation. Are astronomers well set up to deal with model outputs in this form?
Mark, yeah, thanks. This is a really good question. So in principle, in Trieste, I presented a package to deal with those things for some simple aspects of that. But what we really have to think about is to change our databases. In a database, storing a simple mean and a standard deviation value is easy, but perhaps we can find nice representations to be stored in a database and adding that to ADQL to accelerate our queries so that we can phrase a query and saying, give me all quasars with a redshift between 3 and 4 with a probability of more than 95%. So this is really something we have to work on, because machine learning easily allows you to produce something like a probability. But in the end, it's up to us to make use of it. And so far, I figured out a lot of the uncertainties that are measurement errors that are already available in surveys is just ignored. And people don't treat it. They just treat it to cut out certain values. And I think we really have to work on that. Yes.
Okay. Peter Toybin has a question. You could. I'm unmuting.
Okay. Can you?
Yeah.
Yes, I put it in the Q&A, but the question is, can we see the slide again about the CRPS definition?
Give me a second. After I'm on my third computer.
Uh-oh.
Yeah, it's really the third backup computer, and I'm happy I set up so many backups. Yes. Okay, no, I need to share the screen still.
Well, I find it very interesting because we are struggling with the same question of comparing things, and we also discarded RMS and we're trying to do something else. So that's interesting. That I want to have a closer look at that.
There you go. Do you see it?
Yeah.
It's the integral over the Bria score, if you're familiar with this one. And it's in principle, as I try to visually explain, you take the cumulative distributive function of the true redshift. This is a Heaviside step function. It's 0 before the true value, and then it immediately jumps to 1 because it's a point estimate, a point value. And then you take the cumulative distributive function of your prediction, of your PDF. And if you compare both with each other, it's just the surface area between both functions. Peter, does it help?
Yeah, okay. No, thank you. Thank you. Thank you.
Okay, I have one more question from the Q&A. Alex Mashernikov asks, what about point estimates in DNN and random forest models? Did you compare them?
What means comparing? So if you take a point estimate, the point estimate doesn't allow you to do a lot of different things. So if you have a probability density function, you can automatically exclude from a further analysis those where you can't clearly give an answer, those sources where you would have a multimodality. With a single value being predicted, you can't compare it. Of course, you can take the PDFs and calculate something like the root mean square error on it. But as I tried to visually explain, those are scores that don't tell you a lot about the shape of your prediction. So it's always possible to take a PDF and condense it to a mean value and then compare it. But the idea behind a PDF is to give an honest answer about where your uncertainties are, to make you more precise in your answers. And given the multimodalities, a single answer can't be a correct answer because it's not capturing the problem.
Okay, I think we should go on since it's now 12:45, but that's fine. We got to answer all the questions that were outstanding, I think.
Yeah.
So we'll move on to the first talk in the session. So thank you very much.
Yeah, thanks again for your patience getting everything running.
You can unshare your screen. Muted. And so we're now moving into the session. And the first talk is going to be by, let me put on my video since I'm talking. Video. Okay, there we are with my background. Okay, Sergey Banko-Krevrisma is going to talk about deep learning with all of the entire publications of astronomy for the last 200 years. It will be interesting to see what we can learn. Sergio works at the ADASS in Cambridge, although he's probably not there right now. So you can take it away, Sergey.
Thank you, Jessica. So as many as you know, ADASS is a database of scientific articles, especially focused on astronomy and astrophysics. And right now it contains more than 14 million entries and more than 129 million citations. And the core of ADASS is a search engine that is named Apache Solar. This search engine is specialized on textual data, which means that, for instance, it's going to take titles, abstracts, full text of articles, and it's going to go through the sentences and just focus on the individual words of those sentences. And then we could have like sentences like the one that we have in the screen, and it's going to, in the first pass, discard those words that we call the stop words, or those words that are less meaningful for doing searches. And then it's going to count the number of words that appear, the number of times that those words appear in each document in the whole corpus, and also the number of times that the word appear in each individual document. So that by combining these two frequencies, whenever a user searches something in ADASS, the results are going to be sorted with some scoring that is based on those frequencies. One of the difficulties of this approach is that sometimes, in the natural language, there are words that have very similar meaning. Like it could be a cornerstone or fundamental in this example, or sometimes you have exactly the same meaning, but you just have a different spelling between British English and American English. Right now in ADASS, what we do to overcome this kind of limitation is that we maintain a quite large list of synonyms where, when somebody searches something like gravity or gravitational, both things are going to end up searching both words. So a way of trying to improve this and trying to make our lives also a bit easier, maintaining this large list of synonyms, would be like, what if we take all these words and we actually convert them to vectors, so that we have a multidimensional space where we can locate all these words with different points in the different dimensions. But what if even we go farther away and instead of just having all these words converted into random positions in that space, what if we manage to group to distribute them in a way that those words that are more similar, they end up closer together in the space? So we would be transforming these words into vectors and finally what we call semantic vectors. So that's exactly what we've done using a package library that is called Chai, and we've trained we've actually built and trained a neural network with using more than 800,000 abstracts from ADASS, so that now with the help of this package, we can do something different. So we can still start with what we had before, so the frequencies of the words and so on, but now we can look at the corresponding vectors of each of these words, and we can search around the position of those vectors and identify, okay, so when a user searches something, there are other words that are similar to this word that the user has searched. So we can search not only for the exact match that the user has written out. And just to provide an example, more illustrative example, let's imagine that a user searches tidal effects on exoplanets. When we introduce this query using Chai, one of the first articles that appear is this one. And the interesting thing here is that whenever you check the title or the abstract, it's only the word tides that appears, not the word tidal. And we have not, for this experiment, we have not used any list of synonyms. So really the system has learned that these two words have a very close meaning, and it's capable of identifying then documents that are relevant to this search. The same actually happens also for effects, where it appears in the abstract, but only in singular, not in plural. So this is great. So we have all these semantic vectors, but we could even go one step farther, and we could say, what if instead of just focusing on these individual words, what if we actually take the full abstract and we convert that abstract into also semantic vector, so that it captures the semantics of the abstract and in the end the topic of the paper. So we could then have this same multidimensional space, but now instead of individual words, we would have these abstracts distributed. That's what we've done using something called sentence transformers, specifically as SVERT. I will not go into the details. Basically, this is using the language model from Google, named Google BERT, and we've again created a selection of 800,000 abstracts for which we have computed all these semantic vectors, so that we have all these abstracts in this multidimensional space. One thing interesting, having once computed this whole corpus, is that whenever we have now a new abstract that appears, we can easily take that abstract, convert it into the proper semantic vector, and then we can use approximate nearest neighbors algorithms that are, for instance, implemented in the Facebook library named Face, or in a Spotify library named Annoy. We try both of them, and both work pretty well. By having this vector and using these algorithms, we can very easily and very fast scan a large amount of data and identify what other papers are nearby. So this is going to allow ADASS to do a faster and better classification of new articles. Another thing that we can do once we have this data is, of course, apply clustering algorithms, like for instance the typical k-mean algorithm, which would allow us to detect a group of papers that talk about the same topic in an automatic way, just focusing on the content on the semantic content of these papers. So all this is pretty nice, and we've been using all this content, and we've been basing all these experiments on the semantics. But actually, ADASS has more than that, because in ADASS we also have known relationships, as you all know. We know that there are papers that cite other papers, and we have all these relationships already detected in our database. So we thought, okay, then it would be interesting if we can take these known relationships and we can import them into a graph database. Specifically, we are trying Neo4j, and here we imported this data with all these relationships plus other relations, like for instance, this author created this paper, or this paper are about these keywords, and so on. And Neo4j has been shown to be really fast when we do queries, and also the language that is used to do queries on this database, it's a very expressive one. It's a language that is called Cypher. And just to give you an example here, this is an example of a query where everything that is in parentheses, it's like I'm asking for a node. So if we read the query here, we have, I want to match the abstract that has that is identified with the bibcode X, and I want to also identify all the abstracts that this paper cites, and finally I want to identify all the authors that created those papers. So as you can see, with just that single line, very expressive language and easy to parse, we get back all these results that we see on the screen. And when we compare these to things like SQL, you can see that it's clearly more, it's easier to understand and to build a query in Neo4j than in SQL, where you would have to do one or multiple joins to retrieve the same kind of information. So something interesting, once you have all the data in Neo4j, is that you can apply algorithms that Neo4j provides for the data analysis. Like for instance, we can very easily use or apply the PageRank algorithm. This is an algorithm that is going to detect nodes, or in this case, abstracts in our network that have a higher importance. And by this I mean, like for instance, you know that if you go to ADASS and you search for something, you can just sort your results by number of citations. With PageRank, we would not just stop at the first level of citations. Like for instance, if we check the document on the bottom, we see that this document has one citation coming from a paper that has also one citation. But if we compare to the document next to it, we see that same situation. It's a paper with one citation, but it has the paper that is citing has two citations. So in this scenario, PageRank would provide a higher rank, higher weight to this second document. It would consider this more important. As to make an example, or to show an example, this is a query with showing papers from a given author, and we are showing here the computed PageRank and the number of citations. And as you can see, they don't have to correlate. In this case, this author has a paper with some first level citations, but the impact that it has had and the importance that this paper has in this network is higher. So this is an interesting way of exploring the data. Also, something that we can do with Neo4j is apply community detection algorithms like the Louvain algorithm. In this case, again, what we are doing is just by looking at the relationships, the system or the algorithm is able to detect, oh, okay, so we have here like a cluster of papers that strongly cite each other. So, and most probably these papers are related somehow. So we can see some general patterns where papers that talk about stars or papers about cosmology, they tend to be clustered and detected by this algorithm. They are detected together. So I should end up saying that everything that I've shown here, these are really results from things that are not in production right now. These are really preliminary exploration that we are doing in ADASS for future features. So as a summary, we've seen that this can be a very interesting way to use semantic representations to improve or augment the synonym list that we are using internally in ADASS. We've seen that this strategy could also help developing features where we could score documents and articles based on the importance that they have in the graph. And finally, we've seen that this kind of technology can allow us to very fast classify new documents, or even cluster documents that we already have in the system based on the semantic content of them, but also we can rely on the known relationships, so we can combine these two methodologies of clustering and detecting community. So this is all. Thank you very much for your attention. I'll be happy to answer questions.
Okay, first question I'm reading off of the Q&As is how do you translate a word into a vector, and what are the components? That's
a very good question. So there are already algorithms that exist, like word2vect or fast text, that do this kind of thing. What it happens behind the scene is that you train a neural network where one strategy is, for instance, you have a sentence and you just take one word in that sentence, and that word you just convert it to a vector. That first vector is going to be completely random. It's random, but it's within a vocabulary, so that you can always associate your words to concrete vectors, and then that's going to be the input of your neural network. And then you train your neural network so that it's going to predict the words that are around that input word that you've provided. And by doing this kind of training, you can end up using just the hidden layers of that neural network as a semantic representation of your original word.
Okay, then I'll combine two questions and that'll be it, I think. One is, When do you think it will be put into production or in a beta testing mode? And the second question is an interesting one about how does it work with abstracts in languages other than English?
So we have, for the second part, we have not explored yet language models based on other languages, but that's a very good idea and something that we totally should do. And regarding the first question, when it's going to be put in production, so this actually is going to highly depend on how good we do in hiring a new machine learning engineer. As I'm saying here, we are trying to hire, we have a new open position. So it's going to depend how successful we are finding a good candidate, and so that we can give a big push to this kind of project. So that's, I hope it's going to be soon.
We'll close off now and move on to the next speaker. So thank you very much, Sergey.
Thank you.
And check, there are some more questions. Our next speaker is Clara Brasseur, who's from the Mikulski Archive for Space Telescopes, MAST at the Space Telescope Science Institute. And she's going to talk about listening to the stars, astronified, using sonification to get more details out of the data. So Clara, you can take it away.
All right, can everyone hear me and see my screen? It should be an empty screen of Mars right now.
Yep.
All right, and now here's my slides. All right, so today I'm going to talk about a new Python package called Astronify that is for data series sonification. I'm the person giving this talk, but this project is very much a group effort, and we have a core team of 4 people and then are working with too many other people to name today. So what is sonification? The concept behind sonification is simple. It's just representing data as sound. And there are a lot of different ways to do it and a lot of different reasons to do it. But what we are primarily looking at in this project is how to translate light curves into sound in a way where it can be scientifically analyzed. So this is a stellar flare sonified. And Jessica, can you confirm that I properly shared my audio and you could hear that?
Yeah, it came through just fine.
Great. So there are a lot of, as I said, there are a lot of different reasons for doing sonification, from scientific reasons to more artistic reasons, to adding different dimensions. But the core driver behind this project is to increase accessibility, particularly to blind and visually impaired astronomers and future astronomers. And this project is one part of a larger sonification community, and we've been very involved in trying to bring together different people, specifically looking at sonification for astronomy. So there is a monthly sonification world chat that keeps growing. It currently has about 50 people, really from all over the world, so we never get all of the people at once. And we've also been working from the very start with blind and visually impaired scientists and developers, since that is our main goal, is to be useful to those people. We clearly need them to be involved from the beginning, so we're not just writing in our own little bubble. And we're also very excited that there's going to be a Splinter meeting at the upcoming AAS meeting about sonification. So anyone who's interested or is already involved in this work, please talk to me or anyone else and get involved in these things. It's great. So the vision for this particular piece of software was for it to be open source, community driven, and easily integrated into a standard scientific workflow. So the code is on GitHub, the documentation is on Read the Docs. It can be installed locally, and you can easily change, modify, see all the code. So that part is great. It isn't quite, it is open for issues and pull requests, but the initial release is very close but not quite there. We're working out a couple of kinks in our testing infrastructure, and then it will be released, and at that point we will really be able to consider ourselves stable enough to really start soliciting contributions from the community. This is a very new software program. And in some ways, it is already from the start easily integrated into scientific workflows. That was the main driver behind using Python. It is the most popular language in astronomy. So astronomy students and professional astronomers will already be using Python, and then this is just part of that. But because we are part of the MAST archive, we want to go one step further and make this an option right along with the normal or standard give me a FITS file. Instead, give me a sonified file when asking for data from missions like Kepler and TESS that produce light curves. So the design of the software itself, as I've mentioned, this only sonifies data series right now, and so we designed the software to be modular. So currently this is what is there. The main class is the SONI series class that takes in all of the information needed to sonify a data series light curve. And then in future, it would be great to be able to expand to things like spectra, images, all other kinds of data. And so this series class has a data table member. So this is where the user gives in the actual light curve data. And then there's some information that is used to determine how the sonification occurs. So there's a function that takes data values, intakes data values, and puts out audible pitch values in hertz. And then there's some sonification parameters that determine exactly how that happened. And all of these things are used by the workhorse function, which is the sonify function. And that function also puts back the sonified data before it's actually played into the data table. So you can always look at this manually. And then there are two options once your data is sonified. One is to write it to a WAV file on disk, and one is to play it right within your Python interpreter. So what does this look like in practice? Well, here's the all-important SONI series data class. And it doesn't really take that many lines of code, so we can build a small test data table, and without giving it any other information, that means that the SONI series object will use the default sonification function and parameters, and then we can call the sonify function, and now we have sonified data. So if we look at the data table kept within the object, there's the original time and flux columns that we gave it, and now there are two more columns, astronify pitch and astronify onset. So pitch, these are all values in hertz. The human ear can hear between about 20 and I think 20,000 hertz, but for comfortable listening and also because of computer speakers, you want to stay much closer into a much smaller range. So these are all comfortably audible by human ears. And then the onsets are how long after the start each pitch will be played. So then we can call play and hear the sound. And when you do call play, you don't get a plot like I'm showing over here. I did have to put that together manually. You'll just hear the sounds. So this plot is plotting the flux versus time. So those are original data data columns that we put into the object, and then the red cursor will track the play. So that was very short and fairly uninspired. And this is because we didn't actually change any of the defaults. So if we look closer at what the defaults are by printing some of these parameters, we can see that the default time between notes is 1/10 of a second. And the reason that that's the default is that usually when you're sonifying real data, you've got hundreds and thousands of data points. Think about a Kepler quarter long cadence data curve. There's like several thousand data points. And so if you want to not feel like you're actually watching a transit, a planet transit a star in real time, you need to bring the time down. And then each individual note duration is 1/2 a second. So this is why we also get that chord sense. They're overlapping. So we can change these, and we'll take that note spacing up a lot, and we'll take the note duration down just a little bit. So now we can hear the whole thing more clearly. And so we can see in the onsets column that now we're getting 0.2 seconds between notes. And if we listen, it sounds fairly different. So now we can really hear that nice rise, and we can hear the individual notes. But these aren't the only things that we can change. We also use the default pitch mapping function, which is called data to pitch. And it takes in the all-important data array. And it also takes in a number of arguments that all have defaults that we have determined to be sane, basically empirically. And these are the default arguments. So what this is saying is that the output is going to be between 100 and 10,000 hertz. The median of the data will be mapped to 440 hertz, which is the A above middle C for any piano players out there. And that the stretch of the notes will be linear. So we are going to match the stretch. It will be mapped linearly across. And so these inputs are very much like the inputs, and in fact are very much based on the inputs that you would give to an image manipulation function, where you're putting in your actual like electrons per second from your FITS file, and you want to get out something where you can see the features you want to see. And like images, there are reasons that you would want to do it in different ways depending on whether you're like looking at bright stars or the faint limbs of a galaxy or anything else. So if we change these somewhat, so we're going to add some clipping. If we have min-max value, we will clip the upper and lower bits to 2 and 8, and then we're going to bring up the bottom of the pitch range and then move the center pitch up an octave. So we should be able to hear some pretty major differences in the new sonification. And now I've switched to mapping pitch versus time instead of the original flux, so we can really see how this changed. And we can see that we do still have this linear rise, but we now have flat tops and bottoms where we've clipped our values. And then if we play it, we can hear those flat values because of the clipping, and we can also hear that we're definitely getting higher notes, which is great. These are all of the things we set. And so let's play with the stretch now. Depending on what parts of your light curve have different features that you want to hear, you might play around with this. So I'm going to set the min-max value back to none, so we no longer have clipping, and then set the stretch to log. And so looking at the plot now, we can definitely see that this is now because we're mapping pitch instead of the flux. We can see this log shape, and we can also hear it very clearly. So there's a big gap at the beginning, and then it follows a logarithm, and it gets closer together at top. So that's all great, but that's really just test data. So what happens when we actually sonify real data? So here I'm pulling in a test light curve, or building a test light curve using the light curve with a K package. And I'm going to limit myself to about 500 data points, basically just so that it doesn't take as long to listen to. And I'm going to set the parameters the way I want to hear certain features. So I'm taking the note duration down a little bit, but I'm taking the note spacing down a lot. So this is going to scan through the light curve significantly more quickly than default. And the reason I'm doing that is what we're looking at here is the light curve from a heartbeat star. And so with that really fast scan, this is what it sounds like. So I'll play it again in a second, but what you can hear in this sonification is you can hear these large scale features where we have this sort of larger scale periodicity where the range gets big and then gets small. But less can we hear these little, there's all of these little sinusoidal type things that are going on, and they are just all mushed out because we've got this overlapping. We just hear these beating chords. So we can really hear the heartbeat, but we can't hear the small scale structure. So we can change that. So now I'm going to keep the note duration where it was, but I'm going to take the note spacing up by an entire power of 10. And again, I'm just going to sonify even less of the light curve simply for timing reasons. So here we can see that we've more or less zoomed in on this light curve. And we're going to scan across a lot more slowly, so we get, instead of what we heard before, so now we have to wait a lot longer to actually hear this large scale, and it's not as obvious because we're not hearing that fast beating, but we can hear what's going on at a smaller scale. So it depends on what information you're trying to get out, how you're going to want to set these things up. So that was just a brief introduction to this software. Everything you need to know about it can be found on astronify.read the docs. There's lots more examples. There's a test you can take if you're interested in seeing what features you can hear. You can also email us. And if you're coming to the AAS meeting in January, definitely would love to see you at our Splinter session.
Okay. There's one question from Jan Grange. Are there any data repositories around that people can use to make sonifications of paper figures available and linked to the original paper?
Okay, so no, not that I know of. So I know that there is a group in the Sonification World Chat that is focusing on specifically plot sonification, with their goal being that you can basically feed any plot into it and get a sonified version out. I don't believe there's currently any data repositories. One thing that we are working on and that is in the works is collecting information from all of these projects into a central web page where you can scan through and for your use case and see what's being done. So if you're interested in that, email us, and when it's available, we'll send it out. And I do know there is a group looking at specifically paper plots.
Okay, and another question from Rebecca.
Maybe since we are running out of time and we have some people who would like to do some tests of their setup during the break, maybe we can skip directly to next presentation with Colin. Sorry. You can keep the discussion in Discord, but we are a bit out of time.
Okay, so we'll go on to the next speaker, which was Colin Jacobs, who came back to astronomy from software development and politics. Interestingly, he's at Swinburne University of Technology. And he's going to talk about probing neural networks for science. What is it they are learning, which is a question a lot of us have, translating the patterns that you recognize into real science. So take it away, Colin.
Hi, thank you. So I'm Colin. I'm a postdoc at Swinburne in Melbourne. Good evening, fellow Aussies. And I'm going to talk about a case study where we used deep neural networks to solve an astronomical problem and a simple technique that helped us better understand what was going on inside and identify some potential weaknesses. So hardly a day goes by without new papers showing up on AstroPH using artificial neural networks or deep neural networks. And there's a good reason for that. We astronomers have lots of data and they work great. They're almost miraculous at finding interesting patterns in the data. But the more complex the problem is, the harder it is to cover all of the bases in the training set, and therefore to predict the biases and failure modes in your model. like this example, here's a neural network that's great at telling the difference between a picture of a monkey or a guitar. But when you put the guitar near a tree, it thinks it's a bird. And when you put a guitar near a monkey, it thinks it's a person. Very hard to predict those sorts of failures in advance. And this has real world consequences. A deep neural network mistook an overturned truck for a distant billboard, and that led to a horrific accident. Also, maybe it's not life or death in astronomy, but still very important for us. So why is it difficult if you're using neural networks to look inside and figure out what's going on? Well, the models are so large and so nonlinear that any individual part of the input or any individual parameter is likely to have a tiny impact on the outcome. And so it can be, when you've got these days up to billions of trainable parameters, it can be very hard to examine a few and get a good understanding and generalize what's going on and make predictions from that. And if we want to better understand our models, we need something that's both explainable and interpretable. So a tensor of the trainable parameters at one layer in your network would be explainable because it has explainability, because it contains all the information to know what the neural network will do, but it's useless to a human being. You can't look at this and gain any understanding. Something like a plot or a 2D image is interpretable to a human being, but it has to have something that sheds real insight into what's going on in the network. And finding a balance between these two things tends to be quite challenging. So looking at computer vision models, for example, the first attempt to figure out what's going on inside is just direct inspection. So you have a look at the first layer of the network and see what the convolutional kernels are, these things that it's learned to convolve with the input image to detect features. And you learn that it's got an edge detector or something like that, tells you how CNNs work, but not really how your model works itself. You can look at the feature maps. So on the right is what you get when you convolve a particular input with a particular convolutional kernel. And again, we see that it is detecting edges, it's detecting patches of color, but you can't draw too many conclusions. It doesn't help you mitigate this, this combinatoric problem where new combinations of inputs could lead to failures. There's another class of methods to probe neural networks called saliency maps. And broadly, they work by tracing a path back through the network so you can identify parts of the image that are most relevant, so most salient, to making a particular decision. So I took a picture of a gorilla and fed it through some of these saliency mapping algorithms. And you can see that in this example, the gorilla's nose and eyes are important in determining the correct class that is good at gels with our intuition. But is this useful to us as an astronomer, for instance? So my work has involved using deep neural networks to find strong gravitational lenses in the dark energy survey. So here are some examples of lenses that we found. It worked, which is great. A few hundred lenses from hundreds of millions of sources, but it did produce many false positives. Here's what a couple of them look like. Like on the left column there, there's some blue near red objects that aren't lenses. That's understandable. The next column, some false arcs like tidal tails or spiral arms. Again, you can guess what the network is seeing. Some may be lenses, but the signal to noise is too low. But most of the false positives are like the ones on the right. It's just not at all obvious why the network scored that highly as a lens. So it's the galactic equivalent of a monkey with a guitar. So looking at the feature maps of the lens finder, you can see that it's activating on the areas of flux in the image, but that's expected. It could hardly be otherwise. And here's a few more feature maps plucked out from inside the network, the left for lenses and the left for non-lenses. And the only takeaway from this is that maybe there's a pattern there, but explainability and interpretability are really both lacking here. You can't draw many more conclusions than that. Saliency maps may be a little better. Here's a GradCam, that's the algorithm, a saliency map applied to lenses. Okay, it's looking at the red parts are the most salient parts of the input, i.e. the source in the middle. That's expected. So for non-lenses, it's quite different. It's looking elsewhere in the frame when it's making its decision. That's interesting, but that insight only takes you so far. So to extend this, I've been doing something called sensitivity analysis, hoping to get some more usable insights. And this is where we want to ask, how sensitive is the network to some property? In other words, is its performance robust to changes in that property? So as an example, consider a network trained to recognize cats and dogs. We might ask, how sensitive is it to color, for instance? So we can reduce the color saturation in the image and then rescore those examples with the neural network and see whether the network's confidence has changed at all. Maybe the score would drop a little bit when you take color information out. So by systematically varying this property, we can visualize that relationship, and maybe if it makes sense to fit a curve or fit a line to that, and even quantify the effect. And you can do this not just with one example, but with a whole set of examples and do the statistics. So I made a software package that helps you do this analysis pretty quickly. You give it a trained model, a test set, and either a property that you want to test the sensitivity to, or some function that will transform the test set in some way. So it will do the analysis, make a plot, and quantify the effect for you. And so this is from the Journal of Open Source Software, and this is up on GitHub. So for the lens finder, I took two networks that were trained on different training sets and tested several different properties. Some are properties of some are astrophysical properties of the sources, and some of these functions that perturb the inputs. So for example, on the top here on the figure, there's a function that takes a radius and it occludes an annulus of pixels in the input image of that radius. So when you give that to Sensi, it will systematically vary this parameter, the radius, and see how those missing pixels affect the score. And there's some other examples there are convolving with a Gaussian kernel to simulate bad seeing, and adding noise, for example. So here are some results. So what we're looking at in these plots is the mean score in the correct class. So if it's a lens, how highly scored it is as a lens. If it's not a lens, how highly scored it is as a non-lens. And the error bars are a standard deviation. So that tells us how much scatter there is in the neural network's predictions for that class. So here we look at the effect of removing color information by randomly scaling different bands in the image. So on the left, this is for lenses. You can see that the accuracy degrades quite quickly as color information is removed after the effect is, unless the effect is very small, then they basically just devolve to random guessing. For the non-lenses, it's a little bit different. So when the colors are mixed up, the networks appear, the performance certainly degrades, but they appear more likely to conclude the input is not a lens still. So that tells us that color is significant, important if we're going to look at single band images, for instance, and also tells us that it can lead to a bias against lenses when the colors aren't what it expects. Here's the example of that occlusion ring test. So on the right, when you occlude a ring of pixels around in an image that's not a lens, it doesn't make any difference to the score at all. But for the lenses, the performance does degrade, and it reaches a minimum about 1.3, 1.4 arc seconds, which is very typical for a strong gravitational lens that we might discover with this. So if nothing else, it confirms that the network needs some flux at these radii to be able to tell that something is a lens. It's not unexpected, but interesting to be able to quantify that effect. So this was perhaps the most interesting result. This is a test of the point spread function. So for this test, I made new simulations where the simulated PSF was better or worse than the PSF distribution used to train the networks. They were trained on simulations. So a couple of different test sets were used here to tease out the effect. But what we can see is that for one of the networks on the left, which as it happens was the better performing network overall, the performance has a maximum when the PSF mean of the test set is the same as the training set, but it's actually worse when the PSF is better. So this actually turns out to have practical consequences because we made an error when we built the training set. We used a PSF distribution that matched the DES science verification data, but that turned out to be a little bit worse than the PSF in the year 3 release data that we ultimately searched. So looking at this, it seems that we can conclude we probably missed some lenses that we might otherwise have found, because when the PSF is to the network unnaturally good, its confidence decreases. We also looked at, did quite a few tests on the magnitudes of the lenses and the lens sources, so the sources in the image. And here are just a couple of plots. What the left is the R band magnitude of the lens, the right is the G band magnitude of the source. And the takeaway is that, yes, you can see that the performance decreases as the objects get fainter. Of course, we knew that already, but this actually helps describe a bit of a selection function for the neural network lens finder. We can see that, after the lens RMAG is worse than say 21, 21.5, that the accuracy drops a lot. And this is useful because it's very difficult to estimate the completeness of a search. But if we compare this to the theoretical predictions of what we expect to find in terms of distributions of magnitudes, then we can actually have a guess about how complete we're likely to be with a particular model. Finally, here's the results of a test for sensitivity to Einstein radius. So we can see here that the network seems to perform equally well across a whole range of the likely discoveries. Sensi reports that a zero gradient is consistent with this data, so can be quite comfortable that, yes, the training set is robust. We've covered all of our bases in terms of the Einstein radius. So in conclusion, this technique is quite simple, but it gave some useful and quantitative insight into what these networks had learned about strong gravitational lensing. It showed that the Einstein radius was well covered, raised a bit of a red flag with the sensitivity to color. We don't want to be missing out lenses, for instance, that have unusual colors, like a red lens, something that would be great to find. And it helped us find this bug in the training set where the PSF simulations weren't as robust as they should be. So this will help the next generation of lens finders, but this technique is broadly applicable across all sorts of domains. It could work for regression problems, even for unlabeled data. So please, if this could be useful for you, check it out. Yes, I'd love to hear if you manage to get any insights using this technique. Thank you.
Thank you. So it ends. Come on. So this ends the session. We'll be back for the BOF on interoperability of users, developers, and managers, peopleware, at 1 p.m. UT. So thank you for to all the speakers, and we'll see you all later in the conference. Goodbye.
Okay, so again, thanks to all the speakers, of course. I know that there are a couple of people who would like to test their setup. So we have now, as Jessica said, a break until 1 p.m. UTC. Now I know that there is Marcos, for instance, who would like to test his setup for his presentation tomorrow. So I will promote you to panelist. You folks can stick around if you want, or just have a break, stretch, and grab something to eat or whatever. So, okay, we'll wait for Marcos to connect. Marcos, we cannot hear you. You probably have to press the button that says join with computer audio or something like that. Also, Jan, you are the next up with the both at 1 p.m. UTC. If you want to do any test, just let me know. Otherwise, we will.
Can you hear me?
Yep, absolutely.
My two buddies and I are going to do a test, and I think I'll let them take the initiative. Wait a second.
Sure. I'll move again, Marcos. I know. Peter. I'll move Peter as well. So with Marcos, apparently there was a problem with the browser, Safari, and so he's switching to Chrome. Let's see if that works any better. Okay, here is Marcos again. Let's see.
Dus kunnen we nu gewoon praten?
Okay, Marcos, if you want to give it a try, you can just share your screen and unmute and see.
Okay, I just can you hear me? I just unmuted.
Yep, we can hear you just fine.
Okay, let me share the PowerPoint. Let's see if this is working.
Yes, we can see the whole PowerPoint with all the slides and everything.
Okay, I'm going to full screen.
Yep.
Okay, let me quickly navigate to this.
Perfect. Yeah.
Okay, is this? Can you see the movie
Yes,
going on?
we can see. Yep.
Okay, so this is what I wanted to test. Perfect. Okay, so then I can stop sharing.
Fantastic. Excellent.
If I can manage to go there. Okay. Thanks a lot.
Sure.
Bye.
Bye. Thank you. Okay, Peter, if anything you want to try? Do you need me to put you as a co-host? Meaning you would be able to move people to panelists from the audience and stuff. I can do that if you want. That's what I did with Jan at the previous BOF. It might make things easier. Okay, yeah. I see your message on where is that? On Discord, my co-host. Let's see. Yep.
Francesco, can you hear me?
And now, yes, I set you as a co-host. And then you say also Jan, but Jan, I don't see him. Where is he? One person with the hands up. Oh yeah, now I can see him. Oh. And
heard something at the speaker training.
that's good. I still remember that mushroom soup, by the way.
Oh gosh, I'm not sure if bringing it to South Africa is a good idea, but
so Jan, you and Peter are now co-hosts, and so you can
okay, thank you.
Then we
handle
can,
things any way you would like.
and we let other Jan do his what he's good at. So one thing I wanted to test, Jan Noordam, I guess is for you mostly, is dat dit werkt.
This is the
Menti. This is, by the way, the second Menti, but
the letters are very small.
Letters are very small. Okay.
Yeah, but not in Menti.
Not in Menti. What do you mean?
Go to Menti.
Customize. Can I say like big text version?
4, 8, 5, 2, 8.
Oh jee, nou gaat hij meteen al live beantwoord worden. Hey. Ik moet toch eerst even op full screen zetten.
280. Right. Het werkt.
Ja?
Ja, ik zit in Menti, bedoel ik. Ik kijk even naar Menti.
Ja, sure.
Ik ga even de code intypen in de...
Ja, is goed. Dan krijg je waarschijnlijk dus de vraag.
Er is een soort van short URL. Daar ga je onmiddellijk naar de... I should talk English. There's a short URL.
Yes.
It puts you immediately into the
Really?
right link. Yes, there is. I'm going to put it in the...
You're fantastic, Peter. So
Dutch is surprisingly understandable. Not a lot, but you know, it's not too bad.
Sounds like you can make something out of it. Where is Zoom anyway? You have your screen shared. Your Zoom.
Do we have other codes for Menti? There were other questions.
Yes, there is another one. So there's 2 questions in the first one and a 3rd question in the second one. I hope that Jan agrees with me that there's only 3 questions in total. Because if there's more, then I missed one.
Oh, the bubble? Yeah, okay, let me do that one.
It's 4906027. Yeah, you can probably read it better than me saying it quickly.
The letters are very small. I'm not sure that everybody can see them. I read them quickly enough.
No, Jan, that's okay.
It is better? Because they can read it when they have the question open, right? I hope you understand what I mean here. If you go to this Menti link, you will see the question on your own screen at your own size. The question now is actually, is it possible to have...
Oh, that's better.
And the third one?
Well,
is that the third? Oh,
so
what are you? Wait a minute, that's the first one, huh?
There's a second one in the same presentation thing, so that's nice, right? I can just... Already have a raised hand while we didn't even start. So that's the same code, Jan. I'm not sorry, Peter.
Oh.
Of course. It would be good if we would not all 3 start calling each other Jan, because that would make life even harder.
Well, my middle name is Jan, Johannes, if that would help.
You can call me Madroon.
Oh yeah, Madroon, yes. That's also the only way we can actually find you on Discord, isn't it? Or did you change?
Whenever I say something, I expect my picture to appear.
I see you.
Yeah, so what we will do is probably...
Oh, yeah. Oh yes.
Pascal.
Let's do.
Yeah, hi everybody. I'm just testing the equipment, so it works.
Oh, I
fine.
thought you
good.
were going to be our boss.
I'm good. I'm ready for tomorrow.
Oh,
Okay.
Good.
Thank you, guys. You can disconnect me, Francesco.
So now I should probably stop sharing so that Jan can share.
Shall I share?
Yeah, though I have no clue where the stop sharing button has gone.
I can't even see the sharing button.
It's probably because
what kind of user are you, Power?
no, not new share.
Oh, here, share. Oh, yeah.
So Jan,
Yes.
I'm a little confused because you had 2 Mentimeter type selections up, but you said there were 3.
There's 3 questions.
Yes.
But free Mentimeter allows you for 2 questions under 1 code. So what I did is the first 2 questions under the same code. Second question, the third question under the second code. Does that make sense?
We'll see.
We'll see. I mean, I would be very happy to have 3 different codes, but I thought that this was a little bit easier on the audience. I don't know whether that's true.
Can you guys see my screen?
Yep.
Yes.
Would be nice if you could share the that's a full screen, because now I see the slide 1 outline thing on the left. But
so that is Madroon something consultancy. What is the something?
Corporate?
Madroon Community Consultants.
Community.
And your slides are already on the BOF page in the schedule, actually, I just noticed. So the script by Francesco and his team works. And I see a green square somewhere. Am I the only one who sees a strange green square on top of Jan's things, or is it?
No, I see that too.
Stuff? Okay.
How did that get?
What is this thing?
Who's the presenter, by the way? You, Jan? Jan?
Yeah. So how do we get rid of this green square?
I think it's Madroon. Should be, I mean, the presenter, the guy doing all the talking is going to be Madroon.
Okay, maybe I should stop sharing and do it again.
Yes.
Yeah. Why don't you?
If all else fails, someone else does your share, but it's easier that you can do clicks for.
Oh, we have 11 more minutes.
So I thought to do it like this, for example, right? If you want to have this like panelists on the stage experience, just spotlight the 3 of us.
See, Mr. Madroon should have the Dwingelo telescope in the background.
I'm glad enough that I have a minimum that works. I'm not going to be ambitious.
Your working system. I think that's your point, right?
If we do it that way, then I should have the Cyber 7600 in the background.
Well, again, you know the mess in my background. I try to.
Can you see my screen now?
Yes, and there is no green square oddly placed anymore, which is even.
Well, now the green square is around the whole box, so that's that's good, around the whole desktop.
Yes.
But now my arrows don't work.
Because you have to probably click on the.
You have to go full screen. Eh? What is that? There is a button. What is that tool?
Control F5.
Is there a full screen mode for that thing, Jan?
Alt Enter. This is like all the key combinations I know that bring things to full screen, but
I don't know. On my PDF viewer, it's Shift Control F or Shift Control P presentation.
If you are both Linux users, I will leave you to fight out what the right key combination is, because I.
Yeah, but he's using GNOME and I'm KDE, so that's a different tool.
Can you double click the top bar to see what happens? Or right click somewhere on the presentation and see whether there's a full screen in the menu. I guess that's the easiest one.
I should click on the screen and then my arrows work.
Yes.
Good.
Yes. So you could even
Maybe this is going to be working after all.
Yes. And let's see what happens if I want to share my screen now. Okay, then it says this will stop. Oh yeah, okay. So I can forcibly take over the share screen when there is an inquiry, a poll, and then you can forcibly take it back from me again by just clicking share screen, and then it will tell you, are you sure you want to steal the screen from the other? And I just say continue. I didn't do it now because I didn't want to kick you out, but we don't even have to be too courteous and ask each other stuff. We can just do it. That's kind of, I would argue that's kind of good. Then we go here, Discord.
You know, when I was in the POC, I knew more than half of the people on the list, and now only very few.
There's a name for that.
Times are changing. Well, it's good. They're young, brilliant guys and girls. Sorry.
We do have a few now. Yeah. How was that in your time, Jan? The gender balance. Was there a time when it was 100% male?
It was worse than it was now. Yeah. So things have improved.
Oh yeah, there was always one at
still
least.
not very good.
Betty was always there, of course.
Yes, she was very proud because she had been to all the ADASSs.
Yeah,
she had a gold star.
Yeah,
there's already three people who answered the question while we haven't started yet. So people are too interested in the questions to wait until the presentation goes before answering them. 4 people.
So have you guys tested everything you wanted to test?
Well, I have not seen you do the full screen yet. Is that not possible, or?
I wasn't aware that you were waiting for that.
There is a little hamburger menu there. Maybe you can. Right, it's like the 3 horizontal lines, right?
Yeah.
I'm not sure if you're into the jargon enough, Jan.
But what kind of full screen do you want? I'm quite happy with this size screen.
No, I'm not.
Is it very small?
It's manageable, but we don't want to. Do we really want to see how many slides there are still coming? I get anxious about that.
What about this?
You still see the outline.
Well, we know you're not going to do all 46 slides, but still.
No.
Oh, we do.
But now the screen is too large.
Really?
Well, you drop off, Peter, so that's certainly too large.
Oh yes. Oh my God.
You want to remain anonymous, don't you? Maybe a little bit smaller.
Otherwise, you have to go back to where you were before, Jan.
Okay.
Do I hear my echo? Yeah, I do. I hear my own echo.
Is that me? I'll try to mute. And so I think that we agree on saying that it would be probably nicest from the discussion point of view to have people actually raise their hands. But of course, there's lots of people looking on YouTube and some people who are probably better written than verbal.
Yeah,
so
we have to watch both. We have to watch.
We keep an eye on both.
What I'm going to do is I'm going to apologize to the people that we are not quite ready for this kind of online technology. And so maybe that's not very suitable for a proper FADS session, so as we used to have, with lots of feedback. And so, well, they will have to understand that.
Yes, and we'll just say to people, please stick up your hand whenever there is anything you want to say, right? I mean, that's sort of, and we'll you know, if you forget about people having raised hands, that's something that Peter and I can tell you, like, hey, there are 10 people with their hands raised. I think, yeah, I'm totally ready for it. So if I have 4 minutes, I may run downstairs and get a cup of coffee and then come back. And if I break my leg, then yeah. So I shouldn't run too fast.
He's disappearing between the telescopes. So what does the hamburger menu look like, Jan? It's the third button, sort of button looking like from the top right. That little those three little dashes. Yeah, what does it look like? Ah, yeah.
File options.
No, I don't see a full screen there.
Can you see that?
Yeah, I see it, but there's no full screen or whatever we want to do.
No, but there's a full screen in the one of these buttons, but then it's too big, and so.
Yeah, the second button.
I use the entire slide, and so then I can't see the bottom line.
Yeah, this is fine. You can make it as big as you want. Yeah, this is fine. Two minutes.
The crowd is extending. It's 61 now. Can they already hear us?
Yes.
Oh, I should be a bit more careful then.
Oof.
It depends.
My coffee went into the wrong hole.
All right, but now on this, but the attendees cannot say anything because.
No, that's just as well, because it would be very noisy if they were.
But if they put on their hand, are they going to be a panelist?
No, we can choose to let them just speak.
But how do I see that they put up their hand?
I do. Oh, yeah. You have to click on the thing called participants at the bottom of your Zoom.
Yes, I'm doing that. And so on the left, there's panelists, there's 9. And there's on the right, there's attendees, there's 65.
Yeah, nobody's raised their hands right now.
In the panelists, you can. There's an attendee that has raised his hand. Let's see.
Kim was volunteering.
Yes.
She can also volunteer to put the hand down.
Oh, yes. I can see a raised hand with Kimberly Dupree. So that works.
And then she's gone.
Thank you.
And then the options under more, if you click under more, you could promote them, but the other button says allow to talk. And that's what we will use if they can unmute their phone so they can ask a question or comment.
Is that what you do?
Jan or I will do that.
Yes.
Yeah, and you can focus on listening.
Okay.
Yep. We are highly supportive. So just got a message that my family forgot their house key. So in about half an hour, I will run downstairs to open the door. Don't take that as a signal of how the session is going.
I'll be so glad when this is over.
I'll be glad tomorrow.
But we still have the telephone on standby.
Right. Yes, we are good.
Yeah, so I guess we can. I can see the. I can hear the echo. We can start with whenever you folks are ready. With,
yes.
BOF 1143, interoperability of users, developers, and managers. Whenever you folks are ready, take it away.
Okay, I don't see myself on the picture yet. Should I keep on talking in order to be visible?
We do see you for sure.
You see me, okay. Well, that's a good thing. Wait a second.
Well, we see you and the slides.
Yes. All right. Good afternoon, everybody, or wherever you are in the world. Good day. This subject we dealt with last year, but then we had a normal session where we were in a room together and we could actually talk. And I could see who was putting up his hand. That was much easier than we have now. So today you have to bear with us that it's going to be a little bit more messy, and maybe it's not going to be easy to have a good discussion. Because, wait a second, yes. Here's my favorite cartoon, which shows you ineffective managers, users and developers who have not discovered yet that they have wings. And so if we do things properly, then I hope people will discover that they have wings and will be like the birds in the sky that actually can be much more effective. So this is, of course, a Far Side cartoon by Gary Larson, who I greatly admire. So I'll start to say that this session is actually a FADS tradition. We used to have many years ago, on the last Friday of ADASS, we used to have an afternoon where we allowed people to grandstand a bit. So we had a bit of an introduction, and then we allowed everybody to get up and give very profound comments. And somehow software people like that very much. So it was a big success. It was very popular. Of course, nothing came of it, but it was very nice. So today we continue the tradition. Actually, we did this last year already with roughly the same subject. And we would like to do it now. But of course, as I said, with the technological online thingies, it's going to be more difficult to have a decent discussion. So I hope that we can do something. Let's see, do this. So the format of this BOF, hoping that online discussion works. So we have prepared a series of slides that, this is one of them. And we were going to ask you to fill in Zoom polls, but Zoom polls are not part of this technology, so we're not going to use them. But there's some other thing that my two colleagues know about, and maybe that will work. We'll get to that in a moment. We were also going to use Zoom chats, but they don't seem to be available either, which is a pity, because then maybe all the profound remarks from the audience will not be recorded. Well, let's continue. There's some more information. There's a suggestion to turn on your Zoom video so that we can see each other, which gives a bit more of a community idea. Shall I give you a minute to do that?
And Jan, while you're at it, Oleg would like to say something. So Oleg, go ahead.
All right.
No, I just raised my hand, Jan, to make sure you see me, in case you want me to say something.
Oh.
Okay, but you're on the panelists.
Am I on the panelist? Oh, okay. No, I'm not.
Yeah. But okay.
I've got a participant view.
Do you say anything? I can't see your face.
I've got a participant view for some reason.
Oh, should he be a panelist? I didn't know that. I'm happy
Can only the panelists be displayed?
Yes.
This is going to be even more troublesome.
Well, if we had everybody display themselves, that would be a very complicated display. Jan, should we? Yeah, thank you.
I just made him a panelist.
Yeah.
I will also try to spotlight him because it's nice if we can see all panelists, I think. All like panelists who should be talking.
There I am. And there you are. Okay, never mind. Sorry, didn't mean to interrupt.
So, where are we? Is Oleg going to say something?
I've said my piece. Carry on, please.
Did you say something? I couldn't understand it.
I said I've said my piece. Please carry on.
Okay, thank you. Well, the slides that I'm now showing, we will probably not get through them all today. The ones at the end, the latter half is actually a bit of a bonus, and so they are available, and you can download them now or somewhat later. And the URL is here, and but you can ask for me. You can ask me later if you're interested to download them. The polls. Nou ja, Jan Grange will tell you what to do when we get to them. So the target birds of this BOF are 3 groups of people, scientific users of our software, and they are more important than they think, because they are gradually being moved to the fringes by the way we present the software to them, and so they find it more and more difficult to provide feedback, and so they don't, and that's a great pity. That's one of the subjects of today. Then we have software managers, and last year they totally dominated the discussions, and that was a pity because, of course, the developers in the room are much more shy people, and they allow themselves to be pushed away. So please, managers, give them a chance. And so the software developers, it's all about you, really. So speak up within the possibilities of Zoom. Now here we have a poll, and so we can test whether that's going to work. So the idea was that we have you already filled them in?
Well, the link was already on Discord, but
I just put a fresh link in the Discord chat.
Okay, so people are now filling them in. How fascinating! I'm very pleased with this.
But how do we see the results? Then Jan needs a web display somewhere.
Yeah, I can see the result. It's interesting that nobody owns up to being a consumer of science-ready data products, but of course there may be not too many users in the audience, and nobody is bored.
I find it a bit limiting that you can only be one thing. Some of us have to do many things.
No, pick the best. We argued about this too.
So Oleg, what have you put yourself down as?
Well, I said algorithm developer, wishful thinking, aspirational thinking.
All right. I consider you a scientific power user.
I'd like to be a consumer. I would love to be a consumer. Never happened.
Have you now? This is the one that is you?
No.
Okay. Oh, this is fascinating. It's much too fascinating. I can look at this forever. I think we have to move on. So we have a fair number of developers, and I'm very glad that we have a number of people that call themselves support scientists, because one of the points I'm going to make is that support scientists should be also a sort of developer, and we should make it easy for them to be developers, because they can do much more support if they can write their little applications to help and to judge data. And so I'm very glad that there's lots of people in the audience that do that.
Has the poll stabilized, Jan? Has the poll stabilized?
Yes, it looks rather stabilizing. There's already 83 people filling it in. I see some people asking questions. I can't find the link. So on the top of the page, you also see written down that you can go to menti.com and type in the code that's written there. Else, the link is in the Discord that comes with this BOF, which has a very long name. So I tried typing it in as an answer to one of the Q&A questions.
In any case, you've got 84 responses, and I hope this is going to be saved somewhere.
Yes, that's one of the nice things.
That will go in the report. Shall I continue?
Yes, so now you have to reshare your screen and you will be able to
reshare.
Yeah, just share your screen again. Click new share.
Okay.
It will tell you that I am sharing your screen and you can take it away from me.
I have shared my screen. Nothing is happening. Well, you cannot start screen share while the other participant is sharing. Okay, so you guys have to go out first. Can I share now?
Yes.
Ah, here we go again. But now it's very small. Okay, I do this one, and then I share. Good. Okay, this was more than 1 minute, but I think it was worth it. So scientific users, I want to get them out of the way so we can talk about developers. So I really feel that they are more important than they think for the reasons I just mentioned. And so I estimate that very soon 80% of them will be consumers of science-ready data products. And these science-ready data products are going to be produced by huge pipelines that the user certainly cannot touch and very often will not really understand. So that's a pity. So our hopes are on the 10% of support scientists who should really also be can-do developers, and that we should make it easy for them to be like that, much easier than it is now. And 10%, of course, are the power users, and they are the ones that should judge the quality of the results that come out of the pipelines and out of the telescopes. And they should push the limits. And of course, traditionally they have done that, but only a very small number of power users. But we should really take them very seriously, and developers should be responsive to those power users, because that is the way to make progress. Is there anybody who wants to say something about this subject? No.
Feel free to raise your hand if you want to say something, or type it in the Q&A.
Is the person who raises the hand, does he or she automatically go to the top of the list?
Yes, they do.
Okay, so I'll keep an eye on the top of the list. Ah, yes. All right. Oh, yeah, this was a test. Thank you very much. Okay, we continue. Okay, so we have another poll.
That's me. So the strange thing is I can steal your screen sharing. So I think, let's see what happens now. I can probably go here, and then I go to my own Menti, and I can say, because this is of course still the old one, we're already almost at 100.
99.
And the question is, how do I go to the next slide? There we are. And I think that now the question should have changed for everybody who clicks on the same link and or opens Menti with the same code. And I see that one power user already answered. So the Menti power user.
A victim. See, I didn't put
so
it there.
just refresh that last link. Refresh the last link.
Again, the support scientists are excellent. And of course, there's this category of other, but we have no room to investigate them. AT. The testers. I'm very glad that we put in that category.
We're at 91 now. I think we're almost stabilizing, I would say. 92. It's a bit like making popcorn, right? You have to just sort of wait until the when does it stop popping? Well,
actually,
yeah,
this
two
is
pops in a
more
row.
fun than I anticipated. So I'm very glad how this pans out. I think we should move on, shall we?
Yes.
Okay.
Yeah. And
So you will go out and I will share. I will share the screen again. Here we go. And now we share. You know, this technology might actually work in the end. So the full disclosure is that our background is in radio astronomy, which is highly compute intensive, maybe the most compute intensive of all the radio astronomy fields, all the astronomy fields. But the issues, of course, should apply to other fields also, because they also have users and developers and managers. We actually do have an axe to grind in the sense that we have a solution to the problems we're trying to sell. But we would like to hear from you first. So today's premise, because we must always have a premise to focus the discussion a bit. We're talking about data processing software, and that of course is the software that deals with the end product. Many people that write very important software for the infrastructure, and we're not really talking about them. And it's the end product, of course, that that is closest to the user, and so there should be an interaction between the end product people and the users, and they are talking about the same thing. So the kind of data processing software, I thought there were three categories that are important nowadays. One is the enormously juggernaut processing pipelines, and they produce, of course, science-ready data products. And then, of course, there are the science support applications, which are for extracting science from these SRDPs. And ideally, support scientists generate a lot of these applications themselves and share them amongst themselves, not only within the same institute, but also between institutes. I think that should be a very powerful thing to happen. And of course, in addition to that, there are tinkering applications, and these are for the power users and developers to understand what's actually going on in the software and to think of new things. And I have no idea what direction these will take, but I think it's important to create a possibility for them to make it really easy for people to make this sort of tinkering applications and share the results. Is there a category that I've forgotten? If anybody have another one that I should mention here?
Someone's typing on Discord.
Going, gone. So today's premise.
The definition of power users is a question from Discord, which I think is.
Sorry, I didn't understand that.
If someone can give you, if you could give a definition of power user.
A power user. Well, a power user is somebody who is able, in our little world, to use the best features of all the various packages that exist, and put them together and produce unusual results. You know, very deep images of the sky, and really understand what's going on. So they're much more than consumers. They're people who, that are able to push the boundaries. That's a power user. And of course, they're very computer literate. And that's one of the discussions I had, for instance, this morning with someone, that the problem with this field is that the people who are working in it are so competent that they cannot understand the trouble that users have to use their stuff, to do the simpler things, to find the software and to figure out the syntax and to see how it works. So a power user is unusually good at that, and of course can do things that most users cannot, and that's a pity. So the premise is that the field is doing rather well because we have high quality algorithms. You should see some of these results that the new radio telescope produces, really impressive. And for instance, in the last 4 or 5 decades, we have improved the dynamic range with a factor of more than 1 million. And that's a bit exaggerated, 4 to 5 orders of magnitude, but that's still impressive. And we use the latest tools and technology, but the field evolves too slowly because we fail to work together effectively. And that is effectively inside our bubbles and between them. And I'll get to bubbles in a moment. So that's the problem. We're great, but we could move much faster because now good stuff is not reaching the users quickly enough. So the conditions for rapid evolution is short time to market. So new software should be quickly available to as many users as possible. That is certainly not the case at the moment. And short feedback loops, that means that users should interact with developers and not with managers. And there should be open competition. Developers should not be confined to a single bubble, but they should have a chance to interact with developers in other bubbles. And of course, there should be low access thresholds for users to actually use the stuff. And that we can improve on all these in all these areas. So we are held back by what I call a multiverse of bubbles. As far as we are concerned, is that our own software package, our own environment, our own telescope is our entire universe. But in the last 20 years, maybe longer, we have begun to realize that that's not the case, that there are other universes. And so we're actually a multiverse. And so we should try to work together because good users and good developers are fairly rare. And so that limited talent that we have in the world should actually work together better, than we can make more progress. Because the problems we face in our various bubbles are very similar. So we have inefficiency between bubbles and inside bubbles. So that's the premise. Can I offer anybody the floor to say something about that?
I would say that's changing quite a bit, Jan. I mean, I don't completely agree with this picture.
Yes.
There is cross-flow. There is a lot of cross-flow.
Yes.
Certainly more than there was 10 years ago.
Yes. Is it enough?
Well, how long is a piece of string? It's never enough.
Well, for instance, if you look at these pipelines, they use features from different bubbles. And so this is probably what you mean.
Yeah, among other things, yeah.
Yeah, and power users like Reinhard van Weeren, he can use features of different bubbles, and he's very much admired for it. But it's a small minority, and these pipelines, once they have all these bits of different bubbles, they have a fairly severe maintenance problem, because these different things, yes, they do work together, but you have to keep an eye on it, because otherwise it stops working very quickly.
Okay, we have a question from Thomas.
Yes.
So Thomas, go ahead.
Yes,
unmute.
thank you for taking my question. As far as I can tell, the reason for the bubbles needs to be identified, right? It's one thing that I want to break out of my bubble, but another thing that I get paid actually for staying inside my bubble. If I want to break out, I have to do it on my own time, at home, on Sunday evening, instead of spending time with my better half, right?
Yeah.
The other point that I try to raise is that, well, if I develop software, first and foremost, I develop it for the task at hand and not for others. As long as we don't get an agreement with our superiors that they agree, and well, our stakeholders, that they agree, yes, we develop the software not only for ourselves, but for everybody that could be a potential user. Until then, well, the solutions will stay hard to use, will have awkward interfaces that just are usable by the people who wrote the software or who know somebody who wrote the software and so on. So these are two crucial points that I'd like to see to be addressed and identified and figured out.
So can I say that you actually agree with me that it's a problem? The bubble problem?
Yes, but I would take it even further, because you say, yeah, well, we have bubbles. Yeah, but okay, what are the reasons for the bubbles?
Okay, shall I just continue and show you a number of examples of bubbles, and then maybe we can readdress that question?
Maybe we have one more question from Simon. So Simon, go ahead.
Okay.
Hi, yeah, I think we're talking about inefficiency between bubbles. I think it very much, and sort of designing algorithms to be used by other people, it very much becomes about designing interfaces. And it'd probably be a good idea to figure out what those interfaces should look like.
Yes.
I mean, I think probably, you know, the measurement set specification is probably the primary interface at the moment, but perhaps the question is, you know, are there other interfaces that we could think about?
Well, those are excellent questions, and I get to that. You're right that the one interface that we already have and that's very valuable is a common data format, and other fields are quite envious that we have that. But of course, there's also other interfaces like well, user interfaces and ways to jargon and that kind of stuff. So I know that you're working on this stuff. I saw your talk for the RCI the other day. And so I regard you as one of the people who should be part of the solution.
Yeah. Okay. Well, I've got my ideas. I think we're trying it all out. That's the thing.
Okay. But I'm just in the business of identifying a problem, and then of course it's a range of solutions, and but that's the next step.
Okay.
So we agree that there's a problem.
Oh, yes.
Okay, good. We continue. Vladimir Degachev. He's disappeared.
And he can talk now.
Yes.
Oh, hello. Can you hear me?
Yes, we can.
Yeah, I just wanted to add a couple of comments. First, to introduce myself, I'm actually a physicist searching for gravitational waves. So it's kind of like radio astronomy, but at audio frequencies.
Can you talk a little louder, please?
So I'm a physicist working on gravitational waves. So it's like a radio at audio frequencies. So if you guys are in your own multiverse, I got a multiverse of my own and a big bubble inside of it because there aren't too many others. I wanted to add a comment that I think of this bubble kind of like an electrolytic potential. You have two electrodes, right? And if you put two substances in a solution, chances are you'll have some sort of potential difference and some sort of a bilayer forming and so on, which comes naturally. That there are barriers. For example, when I go looking for astronomical data, I need to get images that are different from what I have. And so there is a natural barrier that goes in. Whatever I write is often, as was mentioned, just for the job at hand for the next paper and then goes. And I also want to mention that this is harder for us because there are just fewer of us everywhere, just the market. I mean, how many astronomers are there? If you look at commercial software, the best example of a bubble, if you will, would be the databases. So if you want to set up a MariaDB or MySQL for the older name database, you can just download it with a few clicks on your laptop and just have it running. If you want to set up an Oracle database, even if you have the money for it, you have to hire a database analyst, which is the person who sets it up. So it's it's not that uncommon, even in something that is used by lots of people like databases. And so for us, where the software is really written for the next paper, for the next data set, and so on, I think a bubble is expected and might even be considered to be a feature.
Well, here we run into the limits of our format, because it will be fascinating to go into this a little deeper. I would say one thing is that we talk about identifying a problem and thinking about solutions. And in the solutions, you can also say that you start defining things in great detail, things that people should adopt together, or you can, as an in-between, organize access for people, and then they sort out their interaction together. And I think you are in the third category. You want to already lay down how people should interact without leaving that to them, by just making it possible for them to interact. Is that a fair summary?
I think I just was offering a general comment that the bubbles happen and they're for a reason, and maybe sometimes it's good to take advantage of them. I'm not trying to mandate anybody how they should interact. I certainly benefit from accessibility of data from astronomy, and I use tools like Simbad often and ATNF. So having data online, you start looking for it. If it's available, you learn how to use it. Some of the tools are easier than others. Some are more mysterious than others.
Well, we have to move on. I certainly hope to hear more from you, because the emails will be exchanged. And so I would like to talk to you a little bit more about this. Is that okay?
Oh, absolutely. Would be delighted. Thank you.
Yeah, because unfortunately, all these contributions and discussions will not be recorded. So it will be difficult. People will have to follow up themselves. And so the only service we can offer is that we actually have brought people together and identified people that we would like to continue talking to.
Mm-hmm. Well, Jan, to clarify, what we are doing here right now is being recorded.
Okay. Right. Well, let's... Okay. Then we should wait until we see the record and try to make a summary of it. I will move on. Thank you very much. So a software bubble, as far as I can figure out, is that, here's just a list of some characteristics of a bubble. And the very most important one, often the very most important obstacle between bubbles, is all these different user interfaces. And I've designed one or two user interfaces in my life. It's very amusing, very entertaining work, but people don't thank you for it. And so we have to figure out, we have to somehow overcome that little problem. And of course, different bubbles have their very own operating system, application, programming interface, and software rules, and they're all very good, but they're different. And some of them have their very own data format, which doesn't help at all. We're very fortunate in radio astronomy that we have our data format. And in fact, in astronomy as a whole, we have FITS. In all its humility has been fantastically important. And of course, bubbles are often associated with a source of pride, like a major telescope or a major instrument or a gravitational wave detector. And of course, you know, you like to stay with your source of pride and not get to and surface that as much as possible. And of course, bubbles have emotionally invested developers and users who, would like to work on their own bubble, as some of you have already said. So, anybody else has another other characteristic of a bubble? Garcia.
One raised hand. I can give him the floor. Them the floor. I don't know who it is.
Can you speak loudly?
Hi, can you hear me?
Yep.
That's better.
Yeah, well, I raised my hand before this slide. I just wanted to mention that yes, we are in the situation in which we have different bubbles, because someone else mentioned we have to have common interfaces. I just wanted to mention that having good interfaces is a very tough thing basically to have. So in that sense, it's not unusual that we are in this situation in which several vertical stacks have been constructed, and now we are trying to see the commonalities and how to interface between each other, because having a very good interface from the very beginning will be very tough. That doesn't mean that we don't have to try, and that's, I think this is what we're trying to have here. But I think, the fact that we are discussing this because it's a tough problem. And the other thing I wanted to mention is that one of the things for conditions for rapid evolution, there was a couple of slides before, is a short time to market, but that is a little bit in conflict with good quality assurance. I mean, if you want to have a good product, you have to have a good quality assurance, and therefore you need actually quite extensive testing, and that sometimes conflicts a little bit with the short time to market.
That's very good. That's a point I forgot. It's of course, I consider it implicit, but I think you're very right in making it explicit. Quality assurance is very, very important. And I'm very grateful for you to mentioning the magic word of interface, because as you will find out at the end, that's really what I'm trying to steer towards.
Great.
Okay, we continue. So examples of software bubbles. In the old days, when computers were young, there were packages that were developed by single hero developers, often people with of a grumpy nature and very opinionated. And they used to work together with one or two very hard-working users. And they produced wonderful packages, but of course, they were all different user interfaces, different data formats, different this, different that. And so the good bits were distributed over these different packages. And those packages are now still being, they've been very successful, and they're still being run by these aging heroes, and it gets more and more difficult for them. And then, of course, we have packages by herded cats, between managed groups. You know the expression that managing software people is like herding cats. So I adopted this term. Does everybody identify with that? Do you feel like a cat? You can raise your hand if you do.
You do miss the audience nodding, don't you?
Oh, well, never mind. Let's move on. But of course, apart from packages by herded cats, these packages that are managed, of course, the feedback has to go via the manager, which is inefficient. And on the whole, these packages are not enormously responsive because, unlike the hero developer, there's nobody has sufficient overview to quickly do something. And that's been a problem of these managed groups. And then you have a very interesting phenomenon like the cat that walks by himself. It's a story by Kipling. And so it's a very good term to use here. Because the cat that work by themselves, they often produce very interesting software, but they find it very hard to get adopted by a package or to reach the users. And they find it very hard to be rewarded for their work. And so I think we should pay attention to that particular category. And then, of course, there's the processing pipelines. Those are chains of processing elements that are taken from multiple bubbles. And they are a bubble in themselves. Anybody else wants to propose another kind of bubble? We move on. We have another poll. I think this is the third and last. It's a pity because I started to enjoy them.
Okay, that needs action on me again. Sorry, Jan, I'm
I
taking
put the quick link in the chat.
Good, but I think that people are like real cats. They already answered this question before it became appropriate. It's 26 cats at least over here.
I get paid to develop software for it. That's the gentleman before who said that. Yes, that's of course an important reason to be loyal to your bubble.
While we are waiting, by the way, Jan,
He who pays the piper calls the tune.
I was saying, Jan, maybe while we are waiting for votes to trickle in, I see some people putting comments and our questions in the Q&A. Some of them may not be time appropriate, but just pointing out that you could read them.
Well, you have to do that. Is there anything that you feel that should be addressed?
Oh gosh. Someone mentioning it, it's more of a small herd of cats. Like the open source version of the lone cat. I'll make some comments that the coupling of bubbles to funding is of course a thing that we
It's really, it's so unexpected, the outcome of these polls. I'm very glad that we did them. Next time we'll do more. For instance, I do not understand the question. That's 13 items. It will be very interesting to see why. But never mind, we have no time. We must move on. I'm a bit surprised that it's the bubble of my PhD supervisor, doesn't have more in them. Maybe that's a thing of the past, that the supervisor determined what software you used. Because now it's the supervisor that has to follow the student. Well, once we reach 80, shall we move on?
Okay.
I see a lot of good comments in the Discord, so we can process that later when we write
about
up our
this?
conclusions.
About this one? Peter?
No, in the Discord, I see lots of interesting discussions, comments.
About this particular poll or about other things that we've been discussing?
What we're talking about momentarily and slightly.
Well, that's good. So that is going to be a source of a good summary. All right, so if you guys now leave the poll, then I will, can I share again? Yes. There we are, share. Here we go. Okay, we move on. So, of course, bubbles have advantages because they're sustained by pride and love. All these people who said that they were being paid by the bubble, of course, that's a form of pride and love. And many of these bubbles actually performed miracles. These early packages were really very outstanding. There was some great software being developed. But of course, they have the drawbacks that the good stuff is difficult to combine. It's scattered over the different bubbles. And there's this thing that these bubbles tend to stop evolving for all kinds of reasons. And lack of resources, or just the age of the one developer, hero developer. And then they starve into white elephants. White elephants are products that are difficult to maintain, and they get fewer and fewer users. And it doesn't have to be bad, but in the end, the lack of evolution is the real problem. And that's the premise of today. So I think this is the end of the bubble. Oh, yes. So we have established what bubbles are, and there have been some attempts to escape the bubbles in the past. And one of them that I was closely associated with was the ADASS project, where 7 major institutes, radio astronomical institutes, that ran big telescopes like the VLA and Westerbork, they decided around the early 90s to create a single perfect package that would make everybody happy forever and ever. Of course, that's a very courageous thing to do, but doomed. And so, but we learned a lot from it, and so I'm very glad we went through that exercise. And then, of course, we have another way to escape bubbles is to be a power user, and so you are able to combine features from different bubbles because you're unusually computer literate. And of course, that kind of thing is much easier with a shared data format. But still, it requires special people to do a thing like that. And that's a pity, because then much thinking talent is lost for the cause. And then, of course, there are this modern development towards pipelines. And these pipelines are just modules from different bubbles that are chained together. But the problem is, at least at the moment in these pipelines, is that they have to be designed by specialists who know a lot about these various features that they want to put into the chain. But also they have to, if you look at the definition of such a pipeline, for instance, in the common workflow language, is that lots of the guts of these various things are hanging out, and it's necessary to make these things talk to each other. And that's a major obstacle to maintenance and evolution. So maintenance and other dependency problems are difficult. So the attempts to escape from the bubbles have been, very substantial and done by very good people, but it's still not a solved problem. Does anybody want to say something about this? All right, we move on. So, well, I know, a cat that walks by himself is a Dutchman who's written very interesting flagging and gridding software. And he was complaining the other day that well, he had some of these obstacles that I mentioned here. Of course, you implement your algorithm, and then here you have to test to create a test environment and get some test data. It sounds trivial, but it's usually a fair amount of work. And then you have to demonstrate its superior performance, not only to yourself, but to others, which is also a lot of extra work. And then you have to find a home for it. For instance, you have to get it integrated in somebody else's system, obeying that's somebody else's bubble, or to get it accepted by a popular pipeline so that it's actually being used. And then you have to maintain it for all these other people's systems, and that's some extra work too. And so it's a great pity that the talent of these cats that walk by themselves is actually hindered, not being fully used by all these obstacles that are really, that should not be necessary. So just imagine that all these things would be trivial. How much more productive could they be? Anybody feels like a cat that walks by himself or wants to say something about this?
I see a hand. Vladimir?
Oh, yes. Vladimir, you again.
Yes, I mean, natural, as you might have expected. I have things that I say often, that ideas are reused. Code is rewritten. And I've seen many examples, both in scientific software and especially in open source software. Even in situations where there was a code that did the job very well, I've seen situations where it was written many times, in particular in Linux kernel and other places. The things that actually end up being used a lot and the software that is popular is often the one that is the closest to an idea. So if you think about math libraries that we use, it's really because someplace there was a mathematical model that was devised and that was implemented. Very often I've seen algorithms that people say, hey, I have a great algorithm that would, do something. And when you actually start making use of it, you end up in a situation where it doesn't really provide as much benefit for the effort you needed to do it. It's not close enough to being an idea. On the other hand, I also seen situations where people do not really take an idea that is ready and can actually put it to use.
Yeah, so you feel like a cat that walks by himself. You feel close to these obstacles that I just mentioned.
I would say that the obstacles are a little bit different. It's not so much that it needs to be accepted by other systems, but that there are limits towards people expertise and towards the level of competence in the mathematics that is needed to actually get things implemented. So there is these breakdowns that occur from the past from an idea to an actual piece of code that is going to change.
Is there anybody who would like to say something about this? Well, Vladimir, you should write this because I understand that these chats are being recorded. And I think you can also write them down somewhere. So please do this, and then we'll put it into the report. And I certainly hope to talk to you a little bit more about this.
Okay.
You would have been an excellent participant of these FADS meetings that we had in the old days. Okay, we move on. Pilgrim's Progress, the byline of that book by John Bunyan, is From This World to What Is to Come. I would like to put forward the proposition that we should learn from the runaway success of smartphone apps and the Python universe. That doesn't mean that our software is the same as Python, as our smartphone apps, because they're a little bit more complicated than that. But these two enormously successful schemes, they actually present an interface that makes it very easy to use, for instance, applications. That's for these millions of users. And it's very easy for developers all over the world to present these applications and and make sure that they work because they're disciplined by the interface. And the same with the Python universe is that Python is a small kernel but surrounded by a huge cloud of packages of very high quality that do all kinds of things, and there basically people are disciplined by the Python language, and that also it disciplines them and gives them power. And then again, you have the ease of use by lots of people of all kinds of stuff that they normally would not be able to use, and also lots of third-party developers who contribute. And I think we should study that kind of successes more and see whether we can learn something from them. So, I stick my neck out and say that after the age of bubbles, we could enter the age of the shared interface, and where there's freedom and discipline and feedback and incentive. And well, I'll elaborate that in a few more slides, but if anybody wants to say something about it now? Garcia.
I just want to mention that we are mentioning here smartphone applications.
Can you speak up a bit?
Yeah, you're mentioning here smartphone applications as a runaway success, but I think that smartphones actually they start as its own silos as well in that sense. No? So might not be exactly the best example as something that has a shared interface, and I'm still struggling to see why I can't use the same applications or common interfaces between my desktop and my smartphone. So it's true that they have made a revolution in terms of user interface and how do we interact with our devices. But I mean, people are still struggling to have common interfaces or writing applications which are common between desktops and smartphones. So I'm not sure whether they are the best example in that sense.
Well, I'm not saying that, exactly how you should do it, but I should emphasize that we should look in that direction, because you can see that the two very desirable features there is enormous amounts of users and enormous amounts of developers are somehow achieved. Simon?
And we have a question from Simon. Go ahead. Did I do it right? Allowed. Yeah, go ahead, Simon.
So yeah, I think if we're talking about,
can you speak up also a bit?
Okay, can you hear me now? Am I loud?
Well,
I think in terms of
very close to my microphone and yell into it. I think you should do the same.
I'm going to do that. Okay, I think in terms of the Python ecosystem, definitely what's happened is that all these packages, from my perspective, the common interface is the NumPy array, which is simply a buffer. So almost if we can go to the simplest kind of level, which is like a buffer of data, and write our algorithms to consume buffers and produce buffers, I think that's could be one of the most flexible kind of interfaces that we could come up with. If there are any other interfaces, I'd like to hear.
Yeah, it's true. Python is great. One of my favorite pundits keeps telling me that Python is enough for us, and I try to make the point that we need a little more.
Well, I think it's even more low level than that. I think like the multi-dimensional array, just with raw binary data, it's so simple, and it actually goes back to a C style of programming. If one thinks about it, one is using Python, but it is writing software in a C style fashion. So it might be that in terms of interfaces, we've got to unlearn everything that came from the 90s with object orientation, because that puts abstraction on top of like our raw multidimensional binary data. And I think in radio astronomy, we're actually lucky in the sense that our data is big and just often consists of raw multidimensional arrays. But those are my thoughts on the subject. So I'll give someone else a chance to speak.
I should think that in radio astronomy we have the visibility data are not in rectangular multidimensional arrays. Isn't that a problem?
That can be a problem. There are packages coming out there. Are you talking about in the sense that our multidimensional visibility data can vary by row?
Yes. It's a mess.
So there are, yeah. Well, actually, the thing is, there are packages that deal with this kind of nested data out there today, and certainly in the PyArrow or the Arrow ecosystem, nested data formats are supported, and also now there are packages that like there's a package called awkward arrays, which also supports arbitrarily nested binary data. So the Python ecosystem is developing, and as we speak, and it is probably possible to leverage all this development that's going on all around us.
Yes. Yeah. No,
If
I
we don't
totally
just
agree with
think
you.
in terms of a radio astronomy, if we don't just think in terms of radio astronomy, all these packages are being developed across all sorts of other disciplines.
Yes, and most of them have rectangular data. But the point is that it's the interface that is important because it disciplines and rewards. And I think that's the key thing that we should keep in mind. And so the details will then be figured out by the people that we empower this way.
Right, so it's kind of Marshall McLuhan's "the medium is the message."
Yes.
Yeah.
A small time check. We have 25 minutes left.
No, I think we're doing all right. It's thanks to the difficulties of this communication medium, not too many people chip in. But well, I'm not sure whether the people that are still listening in, whether they're fallen asleep or whether they are listening in fascinated silence.
Oh,
There's no
a
way
lot
to
of them
find
are
that out.
writing.
All right, let's move on. So, enter John Lennon. Imagine a single shared interface with one GUI to rule them all. Imagine a single interface for users that gives one-click access to all compute resources in the world, namely software, including pipelines, data structures, processors, and a second click in the same GUI then executes whatever you are trying to access, provided, of course, you have the right privileges, because some things cost money. But it executes because it knows what to do and how to do it and what to do with the results. That's the kind of ideal that I have in front of my eyes, and that gives huge access to users, makes things very easy, and makes it very easy for developers to offer their stuff to users. So basically, this same, I come back to the same thing all the time. We have to make things easy for users and developers, and then see what happens. So, what I described here in the last slide is a single interface for users, but now the same interface for developers. The same interface that makes your software available to all the users in the world, with this one-click access, and it enables you as a developer to be rewarded. Because of course, this is what I hear from the cats that walk by themselves. They work very hard and they're sometimes very much appreciated and famous, but there's, the reward is very meager for all their hard work. And so this interface makes your software available, but it frees you from all the hassle, and that's of course the carrot and the stick. The carrot is that this interface does a hell of a lot of service for you that you don't have to do. You don't have to provide the content, and the stick is of course the discipline that discipline imposes, because if you don't if you don't respect the interface, then you don't exist. So I think those are two enormously important features. Has this pushed anybody's buttons? Ah, new one. Matthäus. Are you there?
Hello.
Jan, do you have to do something?
Yeah, I was doing something.
Now?
My bad. Something went wrong, and it was because of me clicking on the wrong place on my screen.
Okay, Matthäus.
Can you hear me now?
Yes, if you speak loudly.
Okay, yeah. Sorry, I had to click like three separate buttons. So maybe I misunderstood sort of the first part about the bubbles, but my worry is that having something like the sort of one software interface, it all sounds good. There'd be a perfect world. You just tell, have access to all of the software and just run it without any worry. But my worry is that in terms of scientists as consumers of the software, if anything, that, in my opinion, would put their bubble slightly even further away from, rather than closer to the sort of software development bubble. And it would sort of alienate them in the sense that, things that, say, I always tell, people, friends of mine and people that I work with, things that we already see in for example, deep learning or machine learning, and a lot of introductory courses, it's explained to people that, okay, this algorithm does this. You don't have to really understand what's going on, treat it like a black box. And my worry is that in this case, having something that's just pretty much point and click, as you said, maybe 2 clicks, maybe 3 clicks, maybe just drag and drop like a UML diagram, that puts scientists as consumers of software and the data further away, because they essentially, that becomes a black box for them, and that removes the need to understand what's happening. As I said, maybe I'm misunderstanding the concept, but it's sort of that kind of my main worry, that it will be putting people, further away and actually closing them a bit in the bubble, because that's like, okay, they completely don't have to now understand what's going on behind the scenes. It's really a black box for them. They just, set up something, maybe have a minimum setup, put data in and take data out. So yeah, that's kind of my worry.
Well, you're right, and of course there are many such users, but the users of Photoshop, this program that does image processing, they don't understand what's going on, but it's very high quality stuff that they get, and the stuff is high quality because there are lots of people who think they know better and they start testing it, and they can be very brutal in doing that. And that's why the stuff is so good. So if you make it easy, not only for the users to use it, and then hopefully to trust it, but then also for other developers to compete and to make sure that you don't get away with anything, I think that's going to be a very healthy situation.
Yeah. I think I think it's the case of maybe finding a good balance. As you said, like okay, with Photoshop, people test it, people use it, and most people who sort of push it to the limits test it. I think these are the ones that know their stuff in terms of how to use it, but they don't necessarily have to understand the the exact what I don't know degraining algorithm does or blurring algorithm does. So I think in this case it's yeah the case of finding the sort of right balance between that abstraction that we, as I said, my worry is that at some point we'll go a bit too far.
Well, I want to speak up here. I can't raise my hand because I'm on a panelist, but this is exactly what I've been doing with my main package that I released, which is WCS tools to work with the FITS World Coordinate System and with catalogs and with FITS files in general. And I made it available 25 years ago, and lots of people use it. Not people don't always know that what they're using is something that somebody else wrote, I think. But a lot, the subroutines are pretty, the subroutine library is pretty high level accessible and pretty well documented and stayed constant for most of that time. At least I hear if I change anything. So, having a lot of users, that was always been my argument where I work, that this is something I sort of did on my own, but it's really work too. And I had to justify it. But one of the things I'd use is just the more users I have, the better it's going to be for us. And if you write it well enough, I mean, I don't know if I'd say well, clearly enough, people can actually send you bug fixes when they send you bug reports, which happens to me all the time. Well, too often probably, I guess. So I think I think this is exactly it, you getting it out. But whether it has to be a single universal interface or just a clear interface is, I think, we're at the point where a single interface, I don't think is going to be totally likely, but having a really clear interface will get the software out in the world. And I think that is something people don't always do.
Okay, thank you. I think such an interface is possible, but well, we have a little bit of time to get to that. But so I sense some approval, at least from two people. Shall we move on? Well, you know, the mantra that I just mentioned is freedom and discipline and feedback and incentive. I just play that out a bit, but of course, well, you can read that later yourself. You might be interested in incentives. You know, the incentives you might crave is praise and fame and employment, which, as we have seen, is just important, and also money. For instance, in smartphone apps, you can earn money by the number of people that use your stuff, and that's something that could work in our case too, especially if you make it in such a way that if somebody makes a composite tool that uses your stuff, that you get a part of the proceeds. And I think this kind of possibility is there, especially, you know, it can be administered by the interface if you design it properly. Does anybody want to say anything about incentives? It boggles your mind.
Well, Jan, I could comment that that kind of market economy that you're thinking of, which mirrors the market, it doesn't work right now in astronomy because we're so much based on agency funding, which has a different idea of how we should do work.
But I think the problem is a lot of us who are writing the software are sort of only indirectly based on agency funding. Like we're funded by somebody who's getting agency funding. So they're going to direct what we do to some extent, but not necessarily exactly what we do or how we do it. They want results. I personally like praise and fame, but employment is really important too. So my most fun software I've gotten from, I get it, well, my rewards from praise and fame, but my employment software is usually not as much fun. But on the other hand, having a little bit of praise and fame helps me stay employed.
Yes, that's also it. Well, you
Yeah,
know,
but Jan, on the other hand, both BOFs before you and after you are related to this model, because the one before was talking about citations and the one after talks about how software can be better discovered and measured. And that, like in ADS, could feed back into how many citation points, reference points you get, and that could result into something like money, if you wish. Anyway,
yes,
go on. That's just
there's all kinds of rewards.
Yeah.
And you're absolutely right. If you create a market, it will be serviced. And then things happen that are sometimes also negative, unpleasant. And so I'm not saying that it should be like this, but I think it should be, it is possible, and that might also have some very good benefits.
Mm-hmm.
Because we're talking about rapid evolution of the field. That was the premise that we say, well, no, the field develops too slowly because there's all kinds of obstacles. And money, of course, apart from being an ugly thing, is also a wonderful thing that makes things possible.
Yeah. So we have a quick question maybe from Christoph.
Yes, very interesting discussion. I am doing research. I mean, I am a guy working with interstellar medium. I am doing my own code, but I'm using Python libraries, AstroPy or NumPy or Matplotlib. So I am in between, making some programs, but using also things. And what I want to say is I just don't know what I will need within the next 2 months or next 2 years or within 10 years. There will be new data, new formats, new paradigms, new law to be tested. So I don't think that everything can be implemented under a single button. You say one click, another click. We just don't know what we will put on the second click, on perhaps not even the first one. The next 2 years, because new things will appear. We are always pushing the limits. So I'm not sure that the single interface is a solution, but perhaps more a versatile zoo of interfaces, and with people able to manage them. And I think it's very important not to exclude the 5 sigma events, and something which is just click and click, and a very few clicks will always exclude the 5 sigma events, and the 5 sigma events can bring you the Nobel Prize. So take care of not excluding them. Nothing else. Thanks a lot.
Okay, well, that's why we have to try these things, because you don't know yet what my interface looks like. You think it's going to be a very limiting interface, but that's not necessarily the case. The point I've been trying to elaborate is that we have to move towards some kind of an interface that makes it easier for users to use and for developers to develop and to get these people together. And of course, that interface has to have certain characteristics, but for the moment, we haven't said anything about that. And but I think we are coming to some kind of an agreement. I sense that, maybe that's wrong, that such an interface would be a wonderful thing. Silence. Yes, Christophe?
Yeah, sorry, I was switched off. Yeah, sure. Perhaps in that case, you mean Python?
No, it's beyond Python.
Um,
Yeah, I've got 10 more minutes. Shall I get to it?
Yeah, sure. Show me an example.
All right. Here we go. So, well, that's the summary of the first half of the things that I say that, you know, the interoperability is suboptimal between users, developers, and managers, and between bubbles and inside bubbles. But a single interface offers user empowerment, developer empowerment, and a different role for managers. And such a system is sketched below, and it's called proxies. And I claim that it is cheap and painless to introduce and to try. Now, since at least one person asked for it, I will continue. This is, of course, the cartoon that I showed before, which I'm very fond of. And, you know, you see the inefficient people waddling over the ground, suddenly looking upwards, and to see the efficient people doing great things in the sky. So, these are this is the kind of interface that I would propose, and this is the kind of direction I would like you to think. So proxies are interface objects. In my case, I would think of Python because that's just a wonderful system to do these things in. So they're interface objects that know how to interact with a compute resource. And a compute resource is a software module or a data structure or a computer or whatever you can think of. And so these interface objects, they shield the user from all the things that they do not need to see, because at the moment there's much too much of that. And so smartphone apps and Python in a different way, they shield the user from all the things they do not need to see. But the apps these very simple users actually use are very complicated and powerful things. And the only thing they have to do is to find them with a keyword and then say install and say go. Well, that's the ideal, of course, but we want to get as close as possible to get to there. And so proxies, these interface objects, they have a uniform structure so they can be connected to each other, so they can form networks. And of course, because they have a uniform structure, they can be manipulated by a GUI, which only have to know one structure, that one general structure. So proxies, these proxy interface objects, they represent their underlying target modules, and they can test and execute them. They can offer help and documentation, and they can offer many other interesting services. And they're all controlled by a single proxy GUI. And that's all because of all these proxies have the same structure, and they contain the content that is necessary for them and nothing more. And the proxies can also work unattached, unattached to their underlying target modules. And then, there are very interesting possibilities for simulation and system development. So there are two main proxy types: mono proxies. It's a terrible name, I need a better one. And they talk to a specific compute resource, to a specific piece of software or a specific data structure, or a specific computer, I don't know, whatever. And polyproxies that enable sort of pipelines. The pipelines that we have now are linear structures that just chain together features from all kinds of different bubbles, and as best as they can, they try to hide the details of having to do that. Both types, the monoproxies and the polyproxies, are derived from the same proxy class, so that they can be talk to each other and be manipulated from the same GUI. So here I haven't said anything about characteristics of the interface. Just the important thing is that they all have the same structure. And So a monoproxy's interface to a compute resource, so a software module, data structure, computer cluster. And of course, they use tools like PI and common workflow language and that kind of stuff, because they are very powerful tools, and you don't want to rewrite them or to reinvent them. You know, it's just an interface thing. It uses this stuff, but you don't want the hapless user to actually have to know about PyPI or CWL. It just wants gives the user the possibility to execute it with one click. So these monoproxies do whatever it takes as long as the user is shielded from it. And polyproxies, of course, they interface to one or more other proxies of either kind. So you can have networks of monoproxies and polyproxies, and that can also talk to each other. And the result is so much more powerful than linear pipelines, because they execute possibly a Python algorithm, and they can have loops and conditions and whatever you can think of, anything that you can write down in Python. And so they're much more than linear pipelines. And because the way if you write them, they're much easier to define, because all the guts are hidden inside the proxies. They're much easier, these pipelines, to define and to edit and to maintain. So here's a picture which I hope you can understand. It shows you that the current practice, you have all these, can you see my mouse here? I think you can you? All these compute resources are, for instance, they can be addressed directly by the user or by the CWL pipeline. And in the proxy system, each of these compute resources would have their own proxy here on the right in the oval stuff. And these proxies would be manipulated by the proxy GUI, who manipulates them. And so there you can have one click. I'm getting the idea that I'm not very clear, that I'm not getting through, but never mind. You can see that in front of all the compute resources, there are proxies, and that makes things very much easier and very much more powerful. Is there anybody that I think I should end here, because I can talk a hell of a lot more about this, but we've run out of time. And I'm very interested to see whether anybody has stayed awake to give a comment here.
And the slides are online, so people can dig into it a little bit more at a later stage.
I think they're all comatose.
Oh.
Probably it would be easier to follow with an example rather than so abstract.
Yeah, it's true. I've been amiss there, mainly because, you know, I'm a very poor programmer, as you know, and I'm looking really for someone who can program it for me, because I've been very successful in that in the old days, to find programmers that were much better than me. And that would, I think, very quickly yield to something that people would be impressed with. But as it is, maybe I should try to have it put something clumsy together myself.
Yeah, I was just commenting in the chat to Felix, because he knows that system. This system describing monoproxies and polyproxies in a simpler version, I think, has been implemented in a package called admit, which is a wrapper to Casa.
You should have told me before.
No. I'm just realizing it the way how you explain it here, but in a much simpler way. It doesn't talk about compute resources and so on, but it does have a unified interface, and it allows you also to do a certain operation and implement it in Casa or implement it in IRF. and it's Python based, but it's still much simpler than what you're describing here. You're having a much more powerful interface that knows a lot more about the computing universe. But still, it can build pipelines that way, and it has automatic dependencies and so forth and so on.
All right. Well, you should give me a few more details offline.
Yeah, offline. And I'm not even sure if I'm completely right, because I don't know all the innards of the proxy world. But I'm just seeing a parallel, that's all. And maybe there's other people that say, oh yeah, we've done it this way or that way in R or in Rust.
All right. Anybody else?
There's an interesting question on Discord from James. How would the proxies differ from another bubble?
Don't they, in principle, they cut across all bubbles, don't they? Because all the knowledge about different user interfaces and so on is in the proxies. It makes no difference for me as a helpless user to talk to my own software with its own proxy and somebody else's software with their proxy, because the proxy looks the same. That's the same uniform structure. Vladimir.
I just want to go back and remember something that sounds to a slight degree what you're talking about here, which is a command line interface for Unix, right? So every piece of program, you could start on a command line, and there would be some switches and options that you give it, and then it will do something. And then your proxy GUI would basically involve typing these lines one after another. You can either do it by hand, one at a time, or you can take a bunch of them and just put in a file, and that actually becomes your GUIs that you start, right? So the
yes,
it can read things, it can write things, and it's easily automatable. It's universal, and to a certain degree, it's pretty close to to what you naturally need. It has a minimal thing that makes bubble a bubble, right? So you need a way to start things, you need a way to pass options, and you need a way to automate things. All goes together. And
yes.
the next level of that I personally very fond of is TCL, right? So TCL is kind of like this Unishell that was designed for adding extensibility to other software, so you can hook it up to a piece of code and just run it. And it looks and works very much like those proxies, right? So you can hook up your piece of software in TCL and then bring up modules and string it. And of course, many languages have similar things, but these things were originally designed to do exactly that. So the Unix shell and shells, because there are many different ones, they're exactly what that is to a certain degree. The only thing is that a lot of people now feel fearful of seeing words on the screen, and they want a pretty picture. And I think that's a bit of a barrier. But otherwise, this is exactly what that does to a certain degree, right?
Yes, well, you talk about command line interfaces, and that's exactly what I try to shield people against, because command lines have syntaxes. And that's if you need a different syntax for everything you do, then it gets very complicated. And so I want to shield people against that. But if you say, well, put a number of lines of the command line in a script, then of course you're beginning to get towards a proxy.
Well, I would say that you never go away from syntax. It's just how you express it. So when you express it via command line, you have this enforced format where you have essentially character matrix, right? It's an array, right? One line is one-dimensional array and you have an array of lines, and you put these numbers there from 0 to 255 if you're using ASCII or something more modern, and then you express them that way. If you're having a GUI interface, like for example, Discord or the Zoom, right? Then you still have syntax. For example, at some point I tried to use a chat. Why doesn't the chat doesn't work? Click here, click there. I learned something. So now I know how to use Zoom. I put some comments into the Q&A instead of chat because the chat doesn't work for some reason. I put some comments into Discord. That knowledge will be lost after this conference is gone, because another conference will do it differently, because Zoom will change, Discord will change, you know, everything will change. And there ain't no way for me to automate that error. The same applies to many other things. The cell phones, for example, I'm an Android user, and I can certainly say that it's getting less and less useful year after year. More things are locked down, less things you can do with it. So my comment here is that one really needs an interface that is going to stand the test of time. And you put in a little bit of effort to learn it, which you need for any interface, for any tool. And the more useful tool, the more complicated it gets, and the more effort you have to put in to learn it. Especially if you want to discover new things that other people have not done, which is what we are doing here, right? We all want to do things that other people have not done before, ever.
Okay, well, thank you. I think we'll have to stop it here because we've already run over our time for 10 minutes. I think I would like to thank everybody for participating. And if you like, we can do it again next year. Maybe we'll have a working prototype done, or what's even better, more working prototypes with people of other ideas. So,
well, so I could, when you say a prototype, if you have, there's always the danger of the hero programmer versus the cannot decide because you have 12 people in a team, is that when you put it on GitHub, a design, people can play and tinker with it.
Okay. I hadn't reached that point yet, but we can talk about it. So
yeah,
don't you think we should end it here?
I think that's good.
I think it's been
I
quite
think a lot of people, I hear a lot of people are interested in some kind of toy model, how this would work. I saw an interesting comment on the chat that said, isn't this Corba? Wasn't this done 20 years ago?
Corba.
So maybe in our new
takes me
world,
back.
Say again?
That takes me back, Corba.
Yeah, me too. Dramatically. Well, we can talk about a Tinker model that at least showcase the functionality, and then maybe go from there. I would like that kind of idea.
Well, if we can put a little group together, and that you know, and complement each other in terms that I find people who can program a bit better than I can, then I think that would be a great result of this MOF.
I think that will self-organize itself, Jan. Don't worry.
Oh yes, we. Okay, shall we? I'm actually very tired, so shall we put an end to it and say that we'll look at all the stuff that that's in the records,
yeah,
and try to make some kind of summary. I trust
I
that we
don't
have
know
all the email addresses of the people that have attended.
Yeah, but the Q&A bothers me. There's a lot of interesting comments in the Q&A. I don't know. You cannot grab the whole Q&A. You have to do it line by line, and then I don't get the username in it. I don't know what the trick is there.
I could do a select all, copy and paste in a VI screen, and I think I have.
It doesn't work on my screen. Select all. I only get one person.
Works on my screen. I think one screen is enough.
Okay. All right. You do it.
We'll get there, and I don't know where I'll dump it. Maybe. Maybe
let's do this online. I have no idea whether these people are still here or whether they've gone to drink some tea or something.
Like so, you still claim to be here.
Yes.
So I think we should officially end it so that people can leave, and then we have some time to copy paste.
Yes.
Yeah, this session can end. We shall come back.
Please release me. Let me go.
Anything.
So goodbye, everybody. I'm going to leave the Zoom. Peter and Jan, thank you very much.
Yeah.
Thanks, Jan.
And
thank you. I mean,
thank you, Jose, for doing some magic there.
Thanks for all the LOC magicians.
Stop share.
Stop share.
All right, folks. Thank you so much for the interesting discussion. Fuck.
What happened?
Oh no, I did something wrong myself. Sorry, I did something wrong myself. I don't know what happened, but let's hope for the best. We rejoin at 17 hours, folks. UTC.
Bye-bye.
Bye-bye. I don't see anything, but I trust everything is okay.